So dear friends, good morning. Welcome to the US course 2024 here in Beijing. The US course is specially designed to both users and developers of Opensees, promise to offer in-depth training and insights into the Opensees framework. The sessions are designed to cover a large range from beginners to advanced users, focusing on both theoretical foundations and practical applications in earthquake engineering simulation. The course is scheduled for 2 days, starting from the fundamental to the advanced applications. We have more than 30, you can see here, on-site participants, and more than 70 online participants, because we have a lot of international participants. Many of them are online. And because we have this international community, so that the course will be offered in English. In this morning, the Dimetro will introduce the framework and the scopes of the course. Additionally, Dimetro will still deliver 2 application-intensive lectures covering Opensees PY, that is a Python platform for Opensees, and 3-dimensional structural modeling. In the afternoon, Dieter will present on the linear static analysis of framework structures using Opensees. Following that, we will have a live workshop. Tomorrow, Sabrina, Dimirano, Chu, and Wang, and Pietraka will deliver application lectures and examples. We would like to express our gratitude to all the experts for their valuable teaching and thank all of you for your participation and support for US. If you have any questions regarding the course, please feel free to contact Yong Jiaxu. I think many of them have met him as a handsome young man on the 4th floor to arrange the course. Okay, so let's start. Are you ready?
Yeah, I'm connecting to Zoom now.
Okay, so yeah.
Yeah, very fast. We have 15 minutes for this. Yeah. Okay, good. So we can take some time. I think someone should let me enter. I don't know who is in.
Where is Yifan? Yifan, I think let Christoph go into the meeting room. And I will stop the screen share here. Okay, so you can share screen now.
Okay, I'm inside.
Okay, great.
Recording in progress.
It's running last night, so it's cool this morning.
I should share the screen. Mute my computer. So I think I should use this microphone. Is working as well online, right? Can people hear me online? Hello?
I can try it for you.
Okay. Okay, hello everyone. My name is Cristoforo De Martino. I think someone is using the chat box as well. Welcome also to the people online. Welcome Thomas, welcome Jordan. I like to say their name, and welcome to the students here. It's very nice to be in the first course in Beijing. As you can see, this is the 8th edition of this course. Let's start with some acknowledgement. First of all, welcome to Beijing. I think I'm not a Beijing Ren. I know also Professor Lu is not a Beijing Ren, but now he's adopted by Beijing and the Tsinghua University since many years. For the people here, try to explore the city. The city is very nice, so try to spend your time. I've been many times to Beijing. It's a fantastic city and visit many places. Thanks to Professor Lu. First of all, thanks to Professor Lu. I think it's very good to be here, and it's very good that we are invited here. And thanks to the volunteer. So I would like to say to Yonja thanks, but I would like to say to all the people, thanks. You can see Professor Lu has a very nice website. I would like to advertise this. Please go and visit it. You will find many resources about Opensees, but you will find also many other things about disaster management and now the recently EI design. Thanks to the Euro-Asian Association, EOS. The reason because we are organizing this course is because we have this association. All of us, we are members. We are trying to the European and the Asian side to explain what is Opensees and why to use Opensees. Before to continue, I would like to start with some questions. Who is using Opensees in this room? You. What about other people? Is it your first time? Sound of silence. Don't be shy. So what are you doing with Opensees?
I did apply Opensees to wind engineering.
Wind engineering, very nice. So we can discuss about this later. But in any case, just starting. Let's see also, I would like to share with you the people online. I'm using just starting. So I think it's very good, but I think why we are using Opensees at some point, sorry. So I think there is some delay. So why you are here, part one. I think I will try in this short introduction to discuss why you are here. So any comment about this? Also from people online, I like to read the chat box. Why you are here? Let's see, you. Why you are here? You are the less shy student.
Again, I'm here to learn the development of Opensees on the Python and also try to explore the new thing. I graduated 5 years ago and I stopped exploring Opensees. I want to learn new stuff recently.
You are a very advanced user, but I like the answer we got online by some student, right? The last one, right? I think it's very difficult to pronounce your name. I think it's Azra Tula, right? He would like to model CLT shear wall. So this is what generally is happening, right? You have a supervisor, right? In this photo, you can see there is some delay, but I will try to manage this delay. So you can see there is a supervisor. Generally, this guy is asking you, please use Opensees for your research. Generally, also the background of the supervisor is limited. So this is what happened to me in my PhD, for instance. That's the reason because I start to use Opensees. My supervisor came to me and said, oh, please use Opensees to model blah, 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 something, right? So, and generally, you know, the supervisor first generally, let's say in this generational conflict, right, the supervisor has not a deep background in programming. So, and generally the students obviously start to feel and connect to some website and find information like this and say, what is this? How to use this? So what we will try to do in this course is exactly this, transform this hidden or difficult information in something we can understand more and more. And try to remove this sense that probably you left during the presentation, right? You can see very well the student in front of his computer trying to program, totally frustrated. This is not our first edition. We had more than 800 students in total, I think. I made a rough estimation. On average, we had 100 students, like in these editions. It's the 8th editions. We started with the first edition in Italy, in Rome and Nanjing in 2016. Again, as a game, we start this course because some students asked us to help to learn Opensees. And after that, it was a series of success. Also, you can see in Sicily, in Palermo 2021, you can see all the people with the mask. And the last Opensees conference was in Turin in 2022. You can recognize me together with this gentleman on the first row, Fabio Di Trapani. And you can see here very well that we had a lot of people interested in learning more and more. It's not a huge community, the community of Opensees, but I think it's a quite interesting community. So we have 2 days of fun and learning. So please, let's try to don't be boring. In any case, this is the summer school. We are technically on holidays, all of us. So let's try to make this a less, first, comfortable for us, and second, to be fun. Unfortunately, the only problem I think we will have in this room, we will have not a good sense of the daytime, right? For me, it's good because I'm totally jet lagged. I just arrived yesterday from Europe, so I can feel to be still in the night. But let's try to have some fun. We have the nice introduction by Professor Lu, who is chairing this course and conference. After this, I think we are moving a little bit faster, luckily, to my introduction about the framework. We will start learning some very basic concept of Python and TCL. Then we will move to introduction of 3D modeling of structures. And the afternoon will be dedicated to my good friend, Professor Di Trapani, who will give you the introduction about the non-linear static part. So at the end of this day, we hope that you will learn basically the static part, linear and non-linear. Tomorrow, you will have Antonio Sberna, who will start basically the dynamic analysis of frame structure using Opensees. After, you will have again me with parametric modeling. So we will try to understand how to model in Opensees as a function and then do an update. Update at the end of the day means change some parameters. In the afternoon, we will have these two gentlemen from Xiamen University, who will give an introduction of the geotechnical capabilities. As you know, the geotechnical community inside Opensees is also developed. Personally, I'm a structural guy similar to Fabio and Professor Lu, but geotechnical community is a highly developed community and it's quite interesting what you can do. And in the afternoon, we will have Massimo Petracca from STKO, from, Asdea Software. STKO is the name of the commercial software they are providing, who will introduce you how to implement material, because one of the main characteristics of Opensees is that you can implement whatever you want by yourself. It's an open tool. Different from the commercial classical tools where you don't have dedicated information. And we'll introduce the commercial software from his company, STKO, which I mean is a very good tool for, I would like to say, for very complex model. When you have to model probably simple stuff, we discussed personally with him yesterday. It's probably not the best tool, but if you have to make some very complex with many degree of freedom and many interaction between the parts, probably STKO is the best solution for your research, but you will discuss with him. At the end of both of the days, you can see we have scheduled a live workshop. The idea is that we will provide you some exercises with the solutions. We are not expecting that you will be able to complete the exercise during this roughly 2 hours, but it's our hope that you will start to code by yourself, and if you have specific problems, you can ask to all the teachers here and try to develop the example. So at the end of this, I think someone is still replying what is trying to do. That's nice. So we will learn more and more what is the different application of the community here. Why you're here at this point is the part 2, right? We can move to this. You're here for 2 reasons. First, to be successful in programming in Opensees. We hope that we will transform you from the frustrated guy in front of your computer, right, to an happy kid trying to coding by yourself successfully. As you can see, these 2 photos were generated by ChatGPT. It's funny, you know, because the screen was put on the reverse side, but I think from an information perspective, it's very good because you're trying to code something and you are successfully. And second, that's not a minor problem. Obviously, I can see here that we have more Zhongguo Shuishen, right? We have more Chinese students here. So try to develop the sense of community. You know, when you have problems, that's my feeling. If you have a community with you, you can be successful. Every day when I have problems in Opensees, you know, I'm calling my friends expert in Opensees, and I'm discussing with them, and I say, oh, I have this problem, but not in Opensees, in whatever problem in research. You know, try to develop this sense of community. Try to have more and more interaction as much as you can. As you can see, ChatGPT is obviously biased in another direction. I asked to make a student, right, to make a draw of a student, and obviously we had this white face guy. So, but I mean, that's a minor comment on the bias of ChatGPT. But you can see the key point of the story is please try to make friends, okay? But make friends inside the classroom, online, okay? Maybe you can exchange your email at the end of the course or during the course and say, oh, please contact me, I'm doing similar topics, so feel free to use the chat box as you want. And try to have also friends in the teachers and the people who are here, because the community is the best way to solve your problems. Okay, with this in mind, it's time to start. I think we can start these 2 exciting and funny days. And if you don't have any question, I will start to introduce what I will do. So for the people online, I suggest to use on one side the chat box. I like the idea of the chat box, but if I lose some comment, I think there is a function to write the end, or can you write the end online? No, maybe not. Okay, you can use the chat box. I don't see the other way. Okay, I will try to keep my eyes on the chat box. I think there is someone assisting me here, no, in the room, Xinjiang, in case someone is writing online some question.
Yeah, I think that.
No, I mean, if I lose some question online, there is someone online, or yeah,
Provide help. You check the.
chat box. Okay, there is some question.
Okay.
Please let me know. Okay, thanks. Okay, with this in mind, I think we can start, right? Now, what I want to do, let's see, maybe it's here. No. General intro. No, is this one the general intro? Okay, what we will do today is to try to understand what is TCL. The right way to pronounce TCL is, who knows in this class? TCL. Wow, you are an advanced user. So you should leave this class now, or maybe you should teach this class. Okay, and Opensees together with Python. Sorry, I forgot to update this title. In fact, we have also Python. And we will implement some simple linear structure in Opensees. Okay, let's start with TCL or TCL, right? We have this gentleman, Dr. John Eustentourt. Basically, he was at Berkeley. Everything of this, as you know, also Opensees started at the University of Berkeley. And this guy, you know, created this code called TCL. TCL, let's keep in mind, is not a code for Opensees. TCL is a programming language, very high-level programming language. It's considered a state-of-the-art programming language. But please keep in mind the name is TCL, okay? It's very good because in theory it's a simple language from computer science perspective, right? But if you discuss with people like Dr. Petraka, what do you say? Is a simple language TCL or not? No, it's not. But if you discuss with the computer engineering community, they will say it's a simple language. Okay, who knows how to use TCL here? So let's see the gentleman. What's your name?
Liao.
Lihao. Very nice. What about your typical language? What you're programming in? Python or TCL?
I use MATLAB mostly.
Okay, use MATLAB connected to TCL, I can imagine, right?
Yeah.
Okay, there is also an example I will share with you how to use MATLAB inside to control externally TCL. Okay, that's the way I started. You know, I started exactly like your friend here, by using MATLAB and controlling external TCL. Okay, what is Python? Who is using Python in this class? Also, people online can answer to this question. Nobody's using Python in this class? Wow, only you. What are you doing in Python?
Just basic machine learning.
So what are you using for machine learning? TensorFlow, or you're using something different?
Obviously for optimization.
Optimization using machine learning. Okay, great. So what about other students here? Only you are the guy using Python? No? Okay. What about you use Python, right?
Yeah, I also use that.
Right? Okay, so we found a good student using Python. Okay, but anyway, at some point in this story, let's enter to this gentleman, okay, Frank McKenna. And this, I think, is a very nice story, guys, because how many of you are PhD students here? No PhD students? Only you are PhD? What about other students? I think you are PhD, I'm sure, right? Yeah, so raise your hand, don't be shy, right? So, okay, I think that the funny story, I think, is, you know, Frank McKenna developed Opensees, basically, at the beginning was called G3, and Opensees was developed within his PhD work, you know. So G3 was the solver. So I think this is a good story, guys, because you should remember that in your life, during your PhD, you can probably make something like Opensees. I think it's something big. Yeah, probably Opensees didn't change the world, but it's quite difficult to find a researcher who really changed the world. But please keep in mind that during your PhD, if you work very hard, you can make something like Opensees. Okay, the original version of G3 made by basically McKenna then was acquired by the Peer Center in the United States and transformed into Opensees. Opensees is a good idea, I think, because it's, the first word is open. Who knows what is an open software or open source? So the difference between a commercial software like the software made by this gentleman, STKO, and Opensees is in the key process of compiling. So when you compile a software, basically you transform the human readable information, so what we call coding, into a binary code. I'm oversimplifying the process, but this is what's going on. So when you transform from human readable code into a binary code, basically you lose the capability of understanding the full process. In this way, the majority of the software houses are protecting in some sense themselves. There are more complex stuff, obviously, the way they are protecting. But in an open software, basically you receive the original code or the code adopted before the compiling. So in this sense, I think when you have an open software, you can know all the way the software is functioning. So to give you an example, if you use a software like ANSYS, okay, you can use the elements, but you will never know exactly the formulation, everything inside the software. Because obviously this is a compiled software. When you want to use Opensees, okay, also thanks to the contribution of different researchers all over the world, and also to the contribution of researchers in this list is missing Professor Luxin Zheng, but I think obviously he developed a couple of important elements, especially for the simulation of the high-rise buildings. But thanks to a lot of people, much more than the people described in this slide, we have a large amount of elements, materials for the different application. And for instance, if you think about the last development, also we have the first model. Now I'm entering in the fluid dynamic interaction for simulation of tsunami, thanks to the Oregon State University. But in the future, if you have special needs, for instance, you can propose to the community more and more things. Okay. At this point, I think we had another gentleman. In this case, we are moving to the first Chinese guy in the story, Dr. Mingjie Chu. He was a former PhD student of Michael Scott. Now he's also at Oregon State University. And he developed, I think, to make happy the community, because as you can imagine, TCL is a very lovely language for the people from computer science. But if you ask to a civil engineering guy, I know very well what does it mean, civil engineering and the traditional background in computer engineering, generally it's quite hard to program. So you can see here two very simple examples on the left and right of a code of the same information. We will see in a while the meaning of the different parts, made in TCL and Python. Probably if you look the slide very fast, you will say, oh, they are the same. But this morning I was having breakfast with some person from the South America, okay, and Sofia, and she's a PhD here, and we were discussing about, I'm Italian, the same difference between discussing in Italian and Spanish. So I think they are two very similar languages, but I'm Italian, I cannot speak Spanish. Probably I can understand. So if you speak Ticlese, I will say at this point, right, probably you can understand the Pythonese, right? But you cannot write Pythonese by yourself. So the transition from one language to the other requires some time. Personally, I was similar to the guy in the class, so I was using MATLAB for my research. Since 2021, I totally switched my research in Python. This is not only related to the use of Opensees, but the main reason is for the real implementation of the different things. Because at the end of the day, MATLAB is a commercial software, so this means that it's belonging to a company. That you can have several problems because you should pay the license. Generally, when you use the MATLAB is because if you are a university person, in majority of the case, is because your university is paying the license. But if you want to move to some commercial job, you have to contact MathWorks and say, oh, please, I would like a commercial license. And I can tell you it's very, very expensive. So why, when you want to use Python, you can do whatever you want. Then if you want to have an interaction, I can tell you, with the people of computer science, so people really implementing stuff, if you go with a MATLAB code, the typical reaction is smile in front of your face. Because they are not considering MATLAB as a language. They are considering MATLAB as a software. And this is right. I'm not saying MATLAB is not a good tool. Don't misunderstand my discussion here. I'm not saying please stop to use MATLAB. MATLAB is a fantastic tool. But when you want to move from, that's my personal suggestion, so please take as a personal hint. When you want to move from the academia to the development of real stuff or implementation, but maybe you can also discuss with Massimo Petracca, with the real guy from the industry here, I think that Python has a different value compared to MATLAB. If you want to keep your work inside the research arena, so this means you want mainly publish papers, try your algorithm, MATLAB still is big advantage because in many cases it's easier to program compared to other things. I can tell you, for instance, in Python, to enter in details, you know, you can have conflicts between packages, you have to install everything, while in MATLAB, everything is set. So you install everything, right? You click and everything is working. While for Python, you need what we are calling a little bit more nerd approach, right? So an idea of to be a little bit nerd. Okay, let's start a little bit about the code and information. So here, some information about Tcl. Tcl is a little bit more complex. We can go back to this slide. I think you can have a feeling why it's a little bit more complex. For instance, here you can see we have the setting of the variable of the area. So you should use more parentheses, like you can see you have to use the code like expression. You should use the dollar when you are recalling a variable. While you can see in Python, it's more similar to MATLAB. Everything is easier. I remember at the beginning in Tcl, you know, the dollar for me was a nightmare. But from a real implementation, obviously, the dollar is a good character because it's something you're using to divide when you define something and you are using something. But on the other side, this is let you use whatever character also to define strings and whatever you want in the text. Okay, some brief introduction about what is Tcl and the special character. So I will share with you this material just after the class, okay? So please keep in mind with the dollar, we recall the variables. We have three groups of parentheses, the square brackets, you can see the quotations mark and the curly brackets. And you can see we can use these basically to control the language. We have the escape character, which is the backslash. We have the new line and the semicolon to mark the end of the column, and the hashtag to basically to mark the comment. And that's probably the only character quite similar to Python. So what I mean, if we go back to this slide, if you see when I want to define a comment is exactly the same in Python and Tcl. Okay, that's the general structure of a command. Please keep in mind that a command started in Tcl. So then Dr. Ju moved everything into Python. So the general structure of the command, you can see you have a command name, then you have some sub-command name. Generally, everything is organized in a class structure, we will see in a while. And then you have different options with the different arguments you would like to use. In the case of Tcl, you know, you have a position language based. So this means that the position of each word is very important, while we will see in a while, Python is based on keywords. So you can move a little bit the position because you're using the keyword. So inside the Tcl, the spaces are very important, while inside Python, the spaces are useless because we use the comma to separate through keywords the information. So generally speaking, Opensees is a framework of components, and that's the key successfully idea, I think, in this case. It's different from a traditional way we are coding. Majority of us, it's normal for if you move and discuss about whatever computer engineering program, but generally speaking, you are not the user interface, the language, and so on going down, but you can see you have different parts interacting, and in particular, keep in mind the parts reported in this part here, okay? The key element of Opensees is the model builder. The model builder is the creation of the model, is the basic class. At the moment, we have a single model builder inside Opensees. And the model builder is basically creating the model domain. And the model domain is connecting elements, materials, cross-section, and so on. So when you are starting the model builder, you are populating your model domain. We will see what does it mean, a model domain, by different classes. So you can understand this basic concept? Okay. And basically, we have this. We have a model builder. The model builder is interacting with the domain, and the domain is interacting with the analysis. The analysis, I like to say, is like the play, right? So it's like a time machine. You can move from the step t to the step t plus delta t, okay? Every time you are running an analysis, or step of analysis, you are moving with a time machine into the future, right? It's a prediction. Remember, we are using models and finite element models for structural application to make predictions. Every day, engineers are using predictions. And then we are interacting with the external world with recorder. We will see that inside the Python, this concept is a little bit changed. This is a concept originally developed inside TCL, because nowadays we can read directly the information inside Python and store into data frame, list, and so on, dictionaries, whatever you can use normally inside Python. So this is the key concept. So let's remember, we have a model builder. How many model builders we have at the moment? One, so there is no discussion. You will see the model builder is always the same. With the model builder, we create the domain. The domain is defined generally by two variables. The number of dimension. The number of dimension means how many dimensions has your space. Like we are living in a three-dimensional space. In some cases, you will have you can have 4 dimensions. Who knows who is the 4th dimension? Let's see if we have some geotechnical guy here. Which one? In the soil, what do you think is the 4th dimension? We have Shima there. Yeah, Shima, please. Which one is the 4th dimension? Yeah, it's the pressure, right? Because if you think about the soil, right, you have also the pressure of the water inside the soil, right? And that's an additional dimension. Or if you think, I think we will have the keynote speech of the group of PolyU, of the Sifus Mani, who was before at the University of Edinburgh. They developed the fire module, and the temperature can be a dimension, right? Because each point, right, of your structure can have a specific temperature. So when you're defining the domain, you should define this plus the number of degree of freedom of each node, okay? So plus this, I think you can also store obviously this information in terms of degree of freedom, right? And you can see here that you will have the analysis. With the analysis, you can move of a step t plus dt, and you can see here, you can record the information. So at the end of the day, it seems a simple game, right? We start defining a domain. With this domain, we perform the analysis, and then we can record the information because we are engineers. So for instance, if you are doing a wind analysis, you want to know the value of the bending moment in a column at the base of your high-rise building, right? So you want to save this information. That's the game, and you can see we have different stuff, so we will try to learn a part of them. We have the elements. I think the delay sometimes is a little bit crazy. Now it's good. Okay, we have the elements. So what is that? Who can give me an example of element? What is a typical element? We will start with the simplest one. Which one is the simplest element? Massimo, what do you think? Let's see. The spring. No, the spring is too easy. No, I will start with the truss, right? The truss is I think is the easiest, right? Yeah. Spring, I agree with you, it's the easiest. There is no interaction with the length of the element, right? But in any case, the spring, the truss, the beam, so these are all elements. But we have also shell, we have brick elements, we have a large variety of elements. The element is generally, because today I will discuss with you about elastic materials, is combined with a material. We will see that in the case in the elastic beam column, there is no combination with the material because you can define it only with the elastic, stiffness, right? So then we have the node. So this is the first things you should define, a series of nodes, and connect these nodes with elements and combine this with materials. Then we have the multi-point constraints. We will see a little bit about this when we will discuss about in the next class about the three-dimensional structure. I will show you how to model a rigid diaphragm. We can have the single point constraint, right? These are the normal constraints, fixed boundary, and we have the different possible loads we can apply. And then we have a time series. A time series is generally the way in which the loads are changed with the time, okay? This is true also for static analysis, okay? Please don't be confused about the word time, because many students, I know they are, the typical question, if I'm performing a static analysis, why I'm discussing about time. But time in the concept of Opensees is also step of your analysis. Like if you do a pushover analysis and you increment your load step by step, okay, this can be considered as a time, or if you want in a different word, step. And then you can see we have the different parts of the analysis. Honestly, I will not enter too much given the time constraints. I will show you basic things, and I think also Fabio Di Trapani in the nonlinear part will not enter so much about this, but we have a strong opportunity to change the different solutions. And if you think about special case, also if you need this, if you have special need, you can program by yourself a specific solver. Like in the case of Professor Luxin Zheng, he proposed a few years ago the so-called leapfrog method for the solution of special conditions. So, but in the future, if you have your special needs and you need to solve special problems, obviously you need higher level skills. You will see with Massimo Petracca what's going on. You can solve more and more advanced problem. I will see there are some, well, also online we have some quad. Spring quad, I don't know what is a spring quad. Someone online said spring quad. I never heard well about a spring quad element. I don't know what is a spring quad element. Yeah, I think there is a comma between the two. Maybe you say spring and quad. Okay, okay. With this in mind, finally we have the recorder and so on. Okay, let's start with the first thing. So I will try to connect, okay, online and show you two important websites. The first one is, I hope that in China they are accessible, or I can put my VPN. So the first website you can see, I mean, let me hide, no, let me move here, control. I'm fighting with my computer, 1 second. Okay, so obviously this is the web page, no, sorry, of Professor Luxin Zheng. You can connect here. So this is the web page I was showing you. So it's a very nice web page. You have also the English version for the non-native, non-local people. So, but I suggest you to enter. I connect sometimes. I like to follow his progress and updates. Okay, that's the first important web page. This is Opensees, berkeley.edu. I'm sure if you start to work with Opensees, you know this web page very well. And you have several examples. So why is very important? Because the first question I'm receiving, especially with my students, you know, when they start to use Opensees, is how to use Opensees. So, and generally, you should go to the user documentation, okay, here. So keep in mind this. You go to the command manual, okay? And inside the command manual, you can find all the possible command inside Opensees. So we say that the key element, for instance, is the model, okay? For the model, you can see here, you will find the model. We said we have only the basic builder inside Opensees. And you can see we have the information we were saying before. So you have model, which is the command. This is STICL. We have the sub-command is the basic builder. And then you have the options. In this case, NDM is the dimension of the problem. 1, 2, 3, if you have one-dimensional problem, two-dimensional problem, or three-dimensional problem. And then generally, when you have this, this means that it's an optional parameter. For instance, if you have one-dimensional problem, you have, if you don't define NDF, you have 1 degree of freedom for each node, okay? But you can change this as you want, okay? So another important website is Opensees Spy. Opensees Spy, I would like to say, is a little bit more fancy, but basically is new. I have to say, the Opensees original website is a little bit old-fashioned, right? It looks like a website from the 20 years ago, but I think maybe that was the time when this website was made. I don't know if I can connect to this without VPN. Yeah, let's see. I think it's generally it's working. Okay, or I can connect to the VPN. 1 second. Only 1 second. I think I lost the connect. No, people online can hear me. I don't know if they can see the screen. Okay, I think you need the VPN, but I think majority of the also Chinese students, I know they can. But in any case, you can see Opensees Spy. So keep in mind, we have these two websites, okay? Opensees berkeley.edu. You go to the, let me close this, is not important. You go here to the command manual and you have everything. And here you have, in a similar way, you can see all the commands. You can see if you go to the model, I think we can find probably the same command. You can see if you go to the section 4 first, you can find the same command, okay? Obviously, I think the informations are similar, but are a little bit different. Here you can see that the pre-specified NDM are defined with this equation, but if you solve this equation, you will find the same information. So these are the two relevant websites you should know for finding the common. For instance, if you want to know the elements we have inside Opensees, you can go to here, elements, you can see on the Opensees Spy, and you will find all the information about the possible element. I think that Massimo was saying that the easiest element is a spring. Inside Opensees, a spring is basically a zero-length element. So as you can see, he knows very well the structure of the website. So he said the first one is the zero length. We will discuss about truss element and we will discuss about elastic bin column elements in my class, but you can see you can increase the complexity. You can see going from top to down, and you can have elements as you want. Obviously, in this course, we will not provide a deep background of the finite element theory behind each of these elements. It's my strong recommendation to follow and to attend in your university or in your interest finite element classes, because obviously each of these elements has a theory. And for instance, if you want to use force and displacement based elements for nonlinear analysis, it's important that you have a rough idea of what is the difference. Or if you want to use whatever of this element, in general is good. But you can see we have a large possibility and opportunities of elements, bearing elements. Before some student online was saying the quad elements, shell elements, right? So for instance, please, I don't remember which one is your element, Shinjin?
From the third one to the sixth one.
Oh, from 4 to 6, right?
No.
From 3 to 6?
3, 4,
Okay.
5, 6.
If you want to follow the developments of Professor Liu, I mean, you can follow from 3 to 6. I use these elements. They are elements for modeling reinforced concrete shear wall, where you can have basically different layer of steel and concrete modeling the complex behavior. Again, I don't know exactly the difference of the 4 elements, but if you want to use it, it's highly recommended to study the theory behind. Professor Liu, for instance, has relevant papers in this area. But again, my strong suggestions today is an introduction to Opensees in these two days is to learn and study, first of all, finite elements. And I'm sure that all of your universities are providing very good classes in this sense. So you can see we have also Greek elements with 3-dimensional, you can see behavior. We have tetradon elements. And for soil, you can see we have some special developments of San Diego University for these elements considering saturated soil conditions. Also for interaction between piles and structure, you can see contact elements, cable elements if you have to model, for instance, some bridge with cables. And you can see these are elements for interaction with the fluid. And also we have different elements proposed. But maybe, and that's also our hope in this class, in the near future, you will be able to program your elements and enrich the value of this community. Obviously, all the informations, I mean, to be sure we are on the same page, are propagated or are similar. Sometimes you can find some element is not declared in one part or the other part, or you will find some hidden information in some blog. Sometimes it's quite common for me to find, I don't know, Massimo, is for you the same, to find some hidden information inside the Michael Scott blog, something you don't find public, but you will find as a hidden information, let's say. But in any case, my suggestion is to try to connect to this website, okay, and try to understand. You can see the logic is exactly the same, okay? I hope that at this point is clear, okay, how to think about where to find the information, okay? Let's keep in mind, let's repeat, Opensees, Spy, doc, read the doc.io, and opensees.berkeley.edu. And if you connect to these two websites, you will find the information. Okay, given this in mind, I would like to start with very fast, okay, and simple, okay, concept about TCL. You will find here some basic information. Here you can see all the code are starting with this. Maybe we can compare directly Opensees and Python to save some time, okay? Let's see, I created these two files. All this material will be shared to you, so don't worry. So you can see here, we can compare the two languages. The comment is exactly the same. Remember, we use the hashtag. When we use the hashtag, basically some information will not be read by the interpreter, so you can write whatever you want. If you want to print something on the screen, the command you can see is puts inside the TCL, while in Python we are using the print. Okay, whatever you use the put or print will be print on the screen. Generally, don't ask me why all the course of coding are starting with this hello world. So I repropagated this. But you can see you can also make the comments in different parts, right? You can make an inline comment. In the case of when you make a new line, basically you start a new comment. You can use the semicolon, and this is probably similar between the two languages. You have the basic arithmetic information. You can see you can define a variable. Inside the TCL, we use set house1. In this way, we are creating a variable called 1 with the number 1. In Python, it's much easier. You write house1. You can print the house, I mean, this variable to see the value. You can remove the variable with the unset, okay, inside Python. Let's say inside the TCL, inside Python, you can remove the variable by setting none, or you can delete by del. Okay, but what I want to say is that first, it's very important that you're learning these two languages, okay? In general, here you have some example, okay? Let me show you this example here, how to create a two variables and to sum them. How to create some variables here and sum them. I would like to show you how to run the TCL inside Opensees. If you generally set everything okay in your computer, you digit something like Opensees. Let me zoom a little bit. I am a Mac user, so I will go inside terminal. I think if you are in Windows, it's inside DOS, right? Or something like this. You have a terminal. It's called terminal. Command line is called in Windows. Sorry, I'm a Mac user. Anyway, so when you enter, you can see, you can read the version of Opensees you have installed. I have 330, but I mean, whatever it is. I don't use this here, so it's a little bit old. And you can see, you can basically set, okay, let's try by ourselves. Okay, I can create a variable, set val1, for instance, 3, okay? You can see puts with the $, okay, the val1, okay? And I will receive 3. I can define a second variable, val2, and add this 2, right? And for instance, you can see I can make a division between the two variables, right? So I can divide the first variable, okay, val1 divided val2, and I'm obtaining this number. Oh, what's going on here? Do you think it's right, this? Three divided by 2. But this guy is telling me 1. Or Tickle is stupid, right? Or there is something we are missing. Okay, this is something very nice. Great, Thomas Mang. So, no, I mean, I show you only some example of things where you can handle, okay? Obviously, I don't have the time because we have roughly 1 hour and I have to move to the structural part. But please keep in mind, first step is to learn the language. The key error of people starting Opensees is to don't learn Tickle or Python. If you don't learn Tickle or Python, it's very difficult. Here, the error is very simple. It's because if you write like this inside Tickle, that's a very common error. This as your classmate, I forgot the name online. Sorry, I've seen the chat box now. I forgot. I think it was Thomas, but maybe I'm wrong. You are defining the variables as integer numbers, okay? When you define this as integer numbers, 3 by divided 2 should give an integer results. So the nearest integer results in the Tickle integer algebra is basically 1. So to solve this, okay, you can have val1, you can define 3, okay? Then you can define val2 as 2 point, okay? And at this point, if I am repeating, I'm lazy, so I'm copying this code, you obtain the right number. I can give you a lot of this example, okay? Obviously, we have a time constraint, and if you are interested, please take my email at the end of this class and ask me for questions. But first, if you don't know Tcl, if you want to use Tcl, and you don't know Python, it will be almost impossible to understand the error, okay? So the first hint from here is learn this. I think these two code I will share with you is a simple example. Obviously, Python has not this problem because unless you force to define as integer, I think it's a little bit difficult to define an integer. And I'm not sure in Python, Massimo, maybe, no, I don't think if you divide two integer numbers, you can have an error like this in Python. I think it's impossible.
But it depends on the.
Yeah, I never had this issue, but I think it's more flexible, like, but in, remember, more flexible, that's my experience, means more prone to error. Because when the language is stiff, whatever error you're doing is propagating in a direct way. So like in Tcl, it's quite difficult to override a variable. In Python and MATLAB, it's super easy. In C++, it's very difficult to change the value of, change, for instance, a variable from a scalar to a vector. You have to define, you can. In Python, in MATLAB, it's super easy, right? You click equal and you change everything. So remember, when the language is more stiff, on the other end is returning you many errors, but it's more difficult, okay, to make strange stuff. Generally, for instance, to all my students that are coding something, I'm always recommending them in Python and MATLAB to check the value of the variable at the end of the analysis, because it's super easy to rewrite the variables. Okay, this series of hints, I think, are not solving all your problems. There are other stuff, okay? For instance, if you define a variable A, okay, whatever is the, like here, okay? So this code is setting a variable house, and you can see is calculating, you can see first the sum of a variable A, okay? First we are defining a variable A3, okay? And then we are summing +4, and then we are summing again with the same variable. So this means first here is setting a variable A and with 3. Then is substituting this with 3. Then you have here 4, and then you are summing again the same variable 3, okay? Since Tcl is reading from left to right, remember that if you set like this, is working. If you set like this, it's not working, because the software will say that the variable A is not defined, okay? Again, these are a series of examples, okay? To keep in mind that the first step is to buy or connect online to some resource, buy a book. I mean, sometimes it's a little bit old-fashioned, the book, but there are many books about Tcl and Python, so feel free to buy. And I know also in the Chinese literature, you have very nice books about this. So you should learn and you should understand these things here, okay? Okay, here also some comments about the parentheses here, and you will find here, I will go a little bit faster at this point, the command increment and how to create a for iteration. Inside Tcl, to create a function, the function is called procedure and is defined with the keyword approach. So you can define a procedure, for instance, to plot a certain number. For instance, if you define this procedure, as you can see in line 83, and then you recall in line 86, the procedure with the number 1, you will obtain as an output the number is A. Maybe I can do this to make more interactive, or it means, so you can see if I call this my procedure A, you know, the output of this will be 1, okay? And you can source external file, okay? So for instance, I have another file, bang TCL, okay? And you can see also the local path and the global path. And you can see here, you can, for instance, make the if, okay? We can also run this if together, okay? If I'm setting a variable A, okay, equal to 1, okay? Then you can see here, you can, I mean, this is a switch for language, right? You can, if A is equal to 1, like I said before, right? You can obtain I as output, and I obtain I. If I put whatever number, for instance, set A 0, okay? I recopy the same code, I will obtain, obviously, ni hao, right? So, because it's a different number, okay? And you can have the for loop, okay, in a similar way, X, and so on. If you notice, what is interesting inside Tcl is that basically you never use the equal. So That's the main difference, right? And I think this is the first things make less comfortable this language, right? So when you don't have equal, if you go inside the equivalent Python version, you can see you have a lot of equal everywhere, right? Look about the difference. That's the first difference I can see between the two languages. This equal makes you feel more like what you are studying in traditional mathematics, right? At the elementary school, you're writing A equal 5, right? So you feel more comfortable to what you learn during your schools. But you can see you can do exactly the same stuff. And for me, the main advantage of Python is not the syntax, but is the community behind the game. Because you can find a huge amount of packages for whatever you need. Really, sometimes I'm so surprised about the package for specific functions, not in civil engineering sometimes, searching I can find in the Python community, and is impressive what you can find and what you can do. Okay, these two files, okay, are very important. So if you are beginners, okay, please start from this. Beginners means if for you is 101 Opensees class, please decide your language. My suggestion is decide Tcl or Python. Obviously, now I am a little bit biased, so I will say use Python, but maybe Massimo and this company are still use. Yesterday we had a discussion. We came together from the airport to here by taxi, right, about the speed of the two languages. We didn't reach an exact conclusion about this, but maybe we can share a benchmark with them in the near future, right, to answer to this conclusion. To answer to this question, which one is the faster? But in any case, both are similar. I think you can do exactly the same stuff. So there is no difference. For me, the main difference is that inside Python, it's not the syntax, again, is easier if you look at the syntax. But the key point is that inside Python, there is a large community and you can find package for do whatever. I can tell you a simple example, okay? Tomorrow, I will show you a simple optimization problem of a parametric structure with a genetic algorithm, okay? So we will use a simple genetic algorithm to tune a parameter, okay, of the structure in some sense. So inside Python, if you write genetic algorithm, you can find, I don't know, 100 packages, all very good, you know. I will show, I'm using a package called PyMu, but I mean, there are PyGAD, I know a series of packages by very good developers all over the world. Inside Tcl, according to my experience, I don't know, Massimo, if you know better than me, I think it's difficult to find a package like for this application. In fact, you know, normally users like the gentleman sitting on the second row, right? He was using MATLAB for this special function, right? Because if you go to MATLAB, obviously you can find a series of packages for performing different analysis. Okay, everything is clear at the stage? Yes.
Yeah, I'm Aslan from Malaysia. So I'd like to know the versions of these Opensees in the Tcl and Python. Which one is the latest, or are they the version in the TCL? Python is the latest version. Can you explain about the updating of this software?
Okay, the updating is working obviously from the directly from the Peer Center released the official version. Massimo can confirm there are unofficial version released, right, by several researchers. So what does it mean? You can download the source code. Now the source code is on GitHub. So this means potentially you can, but Massimo will show more details about this. You can download the source code, you can compile your source code, and legally you can distribute from your website. You can change some function. Obviously, you should declare this is my version from Malaysia, right? It's not the original version, right? And you can redistribute it. If you discuss about the official version is released directly from Berkeley University. I don't know if there is a delay between the Python. Now this is a.
They were discussing about making a synchronization between the text.
But they are almost synchronized now, right?
Not exactly. I think Opensees Spy is being released
later.
Later, and more often than the Opensees Tcl. But now they're trying to align it.
Okay, but I think basically they are containing the same information.
Yeah, I think Python version was just a small version I had.
it's more updated.
Yeah.
In the
Like,
Yeah, but that-
but
I mean,
it's
from
nothing
but from
different.
practical perspective, I think if you want to discuss about more details, I think in fact I ask him because he's more in the compiling community. I mean, from practical point of view, there is no difference. No. Except you are really interested in something, will be released just now, but they are quite similar. Generally, I don't know what is the frequency. Maybe you can. What is the frequency?
Before it was like one times per year.
Yeah.
Now it's more frequent. They were talking about making it like every 3 months.
Every 3 months.
Still design. They're still doing decisions.
Okay. So sorry, maybe I didn't say how to install it because we send a document, right, about the installation. So, but from practical perspective, for the Tickle version, first you should install the Tickle. Then you should download basically an exe file. After you have the exe file, there is some Windows tricks, right? You should put in a specific folder and make this folder to be visible from the operative system. For the Python, generally, you can use the pip function. Pip is basically a package used to install other packages. So you did the pip install Opensees Py, and then you have everything set for you. In terms of version, my recommendation is obviously to update. In Python, there are some tricks, okay? Because sometimes you have to update also the Python version. I don't know if there is something similar for the Tickle. There is a minimum required version of Tickle. I know
It's compiled. In Python, Opensees is a DLL.
Yeah.
In Tickle, it's Tickle that is inside.
This is now. Before it was not like this.
It's always been. It's just Opensees is a new interpreter. It's a
Yeah. Okay, so you don't need any specific version. You should only copy paste. Yeah.
But it's not. You need a dependency on Tickle. But
yeah,
the version they compiled it with.
But for Python, sometimes you need to change the version. I don't know. One student, for instance, after they send the email, came back to me, okay, asking for the problem of installing this Python, right? This Opensees Py. And the problem was he had a very old version of Python, probably the original, each Windows machine, has a specific version of Python. So you should update to 3. Generally, my suggestion, I think we agreed also with Massimo yesterday, 3.10 at the moment is the right, because 3.11, I think is not working for instance.
Someone was saying that.
Yeah. So if you have a 2 new version of Python, but if you have some problem in installing, please let me know, okay? But let's say your question is good. From practical perspective, my simple answer is that you can install whatever you want. It's not very different. So let's move to some simple example, okay? So the first example I would like to solve with you is exactly this one, okay? It's the very simple one, okay? It's a truss. You have a elastic material, okay? This is the sigma epsilon constitutive law. Obviously, it's a symmetric material. The truss is has a certain length L, okay? We will build a parametric model. We have the node 1. The node 1 is fully constrained, you can see here. The node 2 is basically a node here, and we have a certain force applied at the node 2 in the axial direction, right? The truss element has a length L, okay, between the node 1 and 2, and is called truss 1. And this truss has a certain elastic modulus and a certain area. I think that we don't have to use Opensees for this. Opensees will be only a tool, right, to understand how to program this. The displacement at the end of the node 2 will be in the same direction of the force F, because the stiffness is positive, and will be equal to FL divided EA, right? We know very well. Okay, how to program this? I think we have some message. The lecture will be okay. Okay, so how to program this? Okay, we can leave this open. We can first start to see the Tickle code, okay? And then I will show you the same. Okay, generally from a teaching perspective, I like to divide the code. I will stand up. I hope that you can hear me online. I think to stay still. Okay.
Microphone that on the back, you can.
Okay. I hope. Okay, I hope you can hear me online as well. You can see here we have generally the title, okay? generally, it's very important to report, you can see here what you're solving, okay, the units. It's very important, the units, why? Who is using Opensees, let's say? Because Opensees is 99% unitless. I'm saying 99% because there are some materials with some units inside, so be careful. But in 99% of cases, it's unitless. So what does it mean, unitless? That whatever you put inside, you will get as an output, okay? There are some tricks, okay? Like, for instance, if you go to the blog of Silvia Mazzoni, who is another important developer in the community, she likes to use these dictionaries with the units, right? It's like conversion factors between units. But in general, my suggestion is declare at the beginning of your code the units. Many mistakes I observed from students is due to units. It seems a simple problem, but many students are doing this mistake. For instance, in this example, I use Newton, millimeter, and seconds. Then obviously, if you use Newton and millimeter, if you have a stress, will be megapascal, right? That's obvious, right? But I think keep in mind, okay, that you have to define these units, right? So if you will have an acceleration, will be millimeter to square seconds, okay? So, but I mean, keep in mind, then you can convert the output, okay? First things is removing the existing model. We use the wipe, okay? At the beginning, always use this wipe. Where you find this function, I mean, to be sure that we are on the same page and then you are independent from me, if you go on this website, I think the wipe should be here, right, in the MISC. I don't search wipe so much. Where is wipe?
At the end.
At the end, MISC.
It's there in command line if you go at the end.
Here?
Yeah.
Wipe here, yes. I don't search wipe so much because it's so easy command, right? So anyway, wipe, you can see here, you have the information, you go here, right? And wipe is basically clearing your memory, okay? So in this way, also, you don't have to restart Opensees, okay? You can simply, okay, continue with wipe. Generally, this is a difference between TCL and Python. My suggestion is to, in TCL, to create a folder and output something. Remember, if you perform an analysis in Python and you don't save something, we will see that there are different ways to save something in Python. At the end of your analysis, you will not get something, okay? So this is very dangerous because sometimes you run everything, right? For instance, an analysis is running 3 days, and at the end of the analysis, no result, right? Remember, you should explicitly save something, right? It's not like a commercial software like Ansys, you know, is saving everything. About this, I think there is some interesting update, probably, especially from STKO, right? They developed a kind of file where you can store everything. But there is also some problem in store everything, right? Because sometimes when your model is huge, also the information stored will be huge, right? So this opportunity to select the specific information that you want to save, sometimes I think it's very good because you can, especially imagine you want to repeat 1 million analysis of one model with 1 million degree of freedom, right? Maybe each model will be 50 megabytes, not so big, right? But if you multiply all this information by 1 million repetitions, right, you will find that the amount of information is huge. So in this way, we can select the information. Okay, generally, I suggest you to have this title, okay, at the beginning, okay? It's very important to specify the units and wipe the model. Then, since I think the main advantage of programming is to make a parametric model, I suggest to have an input section, okay? In the input section, okay, we can define, you can see certain variables. We learned that we can define a certain length. Obviously, this means a first variable L with a length of 5,000. 5,000 what? Let's see if you are sleeping. Millimeters, right? Okay. So then we can select the cross section. For instance, a diameter, okay, is a cross section circular, okay, whatever it is, of 5 millimeter. We select a force to be applied at the end. You can select, you can see some elastic modulus with the variable E. Obviously, you can define as many input variables as you want. And you can calculate here, it was, sorry, there is no inertia, obviously, because the inertia is not useful for the truss, but you can see, you can calculate, as you know very well, the area, right? The area of a circular cross-section is the pi, right? Multiplied by the square of the radius of the circle, right? Okay, at this point, we set basically all the variables. Okay, we can open the same code, okay, inside Python, okay. I think I opened the right one. No, I think I opened another one, sorry. But they're the same. Give me 1 second. Okay, here we change the units, okay, but you can see it's another example where you can feel it's the same. Okay, here you can see the Python, right, again, and you can see the Pickle. Again, I changed a little bit the example. Sorry, I was showing another example. I will add from the one I want to show, but the difference is minimal. You will find all of this in the folder. We define the elastic modulus here. You can see the area in this case is square. You can see, and we have a force. Okay, after we define the inputs, okay, the inputs, please keep in mind these inputs are the necessary one to define this truss problem here. We have to define the model, okay? In both cases, let me open the two parts. The first things we have to start the model builder, okay? What we said in the model builder, we have to say the degree of freedom and the dimension of the problem we are solving. In this case, potentially you can approach as a single dimension problem because it's a truss in one dimension, but I decided to approach as a problem in 2 dimensions, okay? Since it's a truss, basically you have only the force, the actual force, and the transverse force. You don't have any rotation, right? Transverse force, not in the pure truss, but obviously if it's inclined, you can have 2 components. So you don't have to put any force. Any rotation, so this means NDF, number of degree of freedom, equal to 2. So we have to define the 2 nodes. The first node, as you can see, where it's located, you have to define a reference system, right? You can see here, where is located our first node is located, we put our reference system here, 0, 0, right? And the second node, you can see, is located along the X direction, right? With 0, L. Clear? At this point, after the line, these 2 lines here, you can see we have 2 nodes, the node 1 and the node 2, and we have to define what? The boundary conditions, okay? We use the fix command. The fix command is telling if the node is blocked or not blocked. You can see the first node is 1, 1. So you can see here we have a node blocked in both directions. And for the node 2, we keep free the movement in the X direction or horizontal direction, and we keep blocked the transverse direction because obviously the truss is not moving. At this point, what we have to select? We say we have to select the material, okay? In this case, what is the truss we want to model? Elastic material. So in this case, we define the uniaxial material, okay? And we create a material with a certain elastic modulus. And finally, we define the truss. Okay, in this game, it's very important to understand the concept of these numbers here. You can see 1, 2, 1, 2. These numbers are called tags, okay? Like my name is Chris, okay? His name is Massimo, right? Your name is Fabio, right? Reading the tag, your name is Fabio, right? Okay, anyway, so each of us has a name, okay? The numbers, integer numbers inside Opensees, they are called tags and are the name of the different parts. These names should be unique inside each class, okay? So what does it mean? If you are creating the nodes, you have to create a node with different name, okay? If you try to create a node with the same name, the software will give you an error. Obviously, what is the problem? If we have 3 students in the class called Chris, if I say Chris, right, you don't know which one I'm calling, right? And the same problem is inside the code, right? So each node is different. So you can see here we are using these numbers, and then we are recalling these numbers. So this means first we call 1 and 2, and then you can see with the same number we are recalling. Every time you want to recall a certain node, you have to use that name. So keep in mind this because I don't know how is it working in STKO, but I think you can see in your graphic user interface the number of the names. But it's very important also to be smart when you are calling the different nodes, because then you can easily understand where is located this node, especially in complex models. When I'm making frame structure, for instance, but this is something a little bit more advanced, generally I'm creating a kind of special tag, okay, where the different numbers are telling you exactly the location of your frame in terms of base and floor, okay? So then you can easily understand where you are located, but that's a little bit more advanced. Okay, we can fix, okay, this. Then you can see the elastic material again is the same logic. Is missing a small part, right, of this code, but wow. How to make larger? Okay, it was missing this parenthesis. So again, this one and this one is representing the tag. Is a new material. As you can see, this one is the same as this one, right? But this number cannot be the same. So inside this class or inside this object you are using inside the Opensees, you can do whatever you want, but use the new numbering, not the same number inside this class. And then you can see we are creating the truss. And in the truss, this code is basically saying, first create a truss. Okay, here there is no space and no parentheses. The truss is called the truss number 1, is connecting the node 1 and the node 2, which means it's connecting these two nodes here. We have a certain area here, and we have basically the material 1. Okay, so at this point, you can create the loads. Okay, the next section is to create the loads. First, we create a time series in the 2 code. You can see here. The time series is telling you the way for a static analysis, the load in the time is transformed into a load multiplier. In this case, I'm using a linear 1. So this means that if you are at step 1, the load applied will be 1, the loads you are using, the load set you are using, okay? You can use different multipliers. So this means if you reach time 2, you are applying a load 2 times the basic load you're applying in the load pattern. The loads are contained inside the pattern. I say the next step. We have different types of pattern. For applying normal force, you can use the plane pattern. Again, to create a plane pattern, you should define, you can see the time and define the name of the time series and the name. In this case, I'm associating to the plane pattern, you can see the number 1. And you can see here, we are creating the load. At this point, we want to apply a load to the node number 2. So if you remember and keep in mind the simple exercise that we want to solve here, you can see we are applying this force to the node number 2. We are applying this force to the node number 2, okay? And 0 force in the transverse direction. You can see there is a small difference between the syntax of the 2 code. Again, in the taxi yesterday, we discussed about so many things, Massimo, right? So you can see inside Python, generally, you define the pattern, and then you can apply whatever load you want after the pattern. In Tcl, generally you use the curly brackets to put inside the curly brackets all the loads you want to have. So remember, this concept of multiply is applying to whatever load. So what I want to say, if you have a structure, you're applying several loads. All these loads will be multiplied in this way. But you can also define different patterns, okay? You can stop the patterns, you can restart the patterns, you can reset the time. There are more complex stuff you can do in Opensees. After this, we said we want to save something, okay? Traditionally, when I start to work inside Opensees, and then is the main difference with one of the difference, not the main difference with Python, when I was like this gentleman working between MATLAB and Python, the way I was doing is creating a recorder. Recorder is to output the information. You can see here, in this case, we can store several information. Generally, I'm saving for this simple example, the displacement, the reaction force, and the element forces. Sorry, obviously the code is not full, but I mean, I will send you during the break, maybe all this block of examples. And you can see here that we can save some information, okay? And this information is stored in an external file at the end of the analysis. Also about this, there is some more deep discussion, right? You can have this information can be stored at each step of the analysis, keeping the file open, or you can decide to do different stuffs. Or very important, you can connect also to external server. This is also an important function, and you can save the information, or you can connect to different stuffs. Okay, reach this point, we have to define the analysis. For the example, if you want to solve a static structure, okay, basically, always you should use these settings, okay? They are basically the same. Generally, you should define a way to handle the constraints. In this case, we use the plane, which is the easiest one. We use the plane for the way the degree of freedom are numbered. Generally, this is a very computational detailed stuff. You know, speed of solution is depending on the skyline, it's called of the matrix. So if you want house parts, it's the matrix. So if you want to, in other words, if you have many elements far from the main diagonal, right? If you have a full diagonal system, it's solved line by line, right? So that's faster. So there is some series of algorithms to speed up this. Then you have a system is the way you are storing the information. And then you have to create an algorithm. In this case, we are solving a linear structure, right? It's a simple elastic modulus. We want to solve a load control problem, not a displacement. We have these two basic ways to control. In theory, we have also different types of control, but basically load control, because this means we want to know the displacement when you increase the force to a certain point. You can also solve the inverse problem. You want to know a certain displacement level given a certain set of forces, okay? That's what we are doing, for instance, in many cases in pushover analysis, right? So we apply a force and we want to reach a certain level of displacement. And we are solving a static problem. I think it's clear where we are applying the time, and we are performing one step of analysis, okay? And this step of analysis is made with, with this analysis, one step is made with by increasing the time of one. So this means we are moving from the time 0, no forces, the multiplier of the forces is 0, to the time 1, where the multiplier of the force will be equal to the force applied to the set of force applied to the system. Okay? At this point, after we finish the analysis, okay, this block basically will be copied in all the examples I will show you in the following, is exactly the same. Obviously, if you move to a nonlinear problem or you move to a displacement-based problem, you should change this a little bit. But if you want to solve a elastic structure, whatever it is, you can copy-paste this without thinking so much. Obviously, you should change the number of steps in this if you want to make a different solution. And finally, generally, at the end of the analysis, what I'm suggesting, is to make a kind of screen print, okay? In this case, the TCOL code is ending faster. Always, this is what I'm telling to whatever student running a finite element analysis with Opensees or with whatever complex stuff, always keep in mind to have a number to compare, right? In this case, we have the exact solution, right? But generally, also if you run a super complex high-rise building with a certain, compare with an equivalent beam, something like this, okay? Because you should have something to know if your number makes sense. Remember, a finite element software will generally, removing minor problems, always will give you a kind of solution, right? Then if this solution is right, it's your problem. It's not a problem with the machine. We will be jobless when the machine will tell us if the solution is right or not. It's our job now to tell if the computer is giving you a solution making sense or not. Still also when I think Shingen can also say something about your progress in the artificial intelligence for structural design. Still it's a human problem to say if the solution provided by the machine makes sense or not. So when this will not be our job, probably will be fully jobless at that point.
Someone has to record the lesson.
Yeah. I think we or they are recording. Okay, I didn't check. I don't know. We didn't discuss about this. Maybe we'll discuss during the break about this. Now it's better to be.
Somebody
Yeah.
asked question and we answer that if with the permission of the teacher,
Yeah, for me, it's fine. For me, no problem. I don't know if.
Anyway, you can go on.
Yeah. For me, it's if you want to record, you can. Okay, so for me. Okay, here we have the displacement, okay? And we are having, you can see, a comparison with the solutions we know. Okay, we can try to run, okay, this code. And finally, I will show you also another things very important. In this case, a progress coming from Poland about this OPSVs, okay, the package to post-processing the results inside Python. Okay, let's try to run together, okay, this code, okay? And let's have a look. In this case, it's very easy, okay? If you want to run here, you can digit Opensees, right? And I mean, I think in Windows it's the same, right? If you drag and drop the TCL file here, right? You will have the path, right? In Windows it's the same, right? No?
Never test.
Never tested, so convenient, right? So you drag and drop, right? You click, or in any case, you need to copy the, I mean, in this case, I'm using the full path, okay? You copy, you run, and you can see you have the displacements here copied, okay? And you can see that the displacements, okay, they are reported in a different way. Here you have e to -7 are exactly the same, okay? So if we change a little bit the code, okay, and we say let me put here, right? You can see only to show you real time that we can modify this code, right? We can add puts, okay. Professor Luke is my favorite, right? So we can save, you can see I can run again, Opensees. We can copy this here, right? So if everything is right, you can see, you will read the Professor Luke is my favorite, okay? Okay, only to show you that at the end of the analysis, if you saved in a proper way, okay, all the information that you need, you can export everything. Okay, let's see how to run everything inside the Python. Generally, there are many ways to use Python, a lot, I would like to say. In my case, I generally use Spider. Again, why I'm using Spider? Because before I was a MATLAB user, and Spider is the most similar environment. If you discuss again from a guy from computer engineering, you will say that Spider is a disaster, right? Generally, Massimo, you're using VS Code. What is your platform? So it's for Python. Visual Studio directly. Okay, we have to say that the Spider is running IPython, so it's not exactly the Python environment. IPython is similar. What is the name of the other one? Now I don't remember. What is the Python? Massimo, help me. The Python, when you run the Python inside the browser, you don't use it probably. Jupyter, yeah. Jupyter is exactly IPython, yeah. Now I don't remember, my mind was not remembering the name. So and the difference is that the kernel is always on. When you run Python, generally you start the kernel, so this means you start Python. And at the end of the process, unless you do some trick, Python stops. Here is like you have a kernel always operating. It's never stopping, and it's similar to Jupyter. So that's the main difference. This is producing some big issue because when you want to run real-time process, you have problems in this case. Or you want to use a scheduler, the stuff here is not working. But let's say from academic perspective, I like it because in a very simple way, you have the code here. Maybe I can zoom a little bit. You have the console here. Very nice. I like this idea to have the table of content or the index of your code. So also when the code is complex, you can go back and forth. If you use the 2 times %, you can create this index. And I run now the code. You can have all the variables defined here. You can see I have an area. I can read easily here. You have the base. You have all the stuff here. Okay. Here you can see we have this displacement. Okay, provided here is the same number. Obviously, we provide from the TCL. You can see here, modify a little bit the code, right? And have print, again, we can make Professor Luke is the best in this case. If you change this, you can see we have Professor Luke is the best, but you can also check here directly. You can have OPS. If you click the tab, you can see here, you have all the functions directly inside the Python provided here. This is very convenient, right? Because without getting crazy with the manual, right? For instance, if you want to know the displacement, okay, of a certain node, right? So I want to know node disp, right? I digit node disp, node 0, right? What is the error? Because it's node 1, right? You can see the displacement of the node 1 is obviously 0, 0, right? You remember the node 1 is the node blocked, right? We block the node 1, right? And the displacement of the node 1 is equal to 0. If I want to know, for instance, the displacement of the node 2, right? You can see I have the displacement in the x direction is the small number here to -7. The displacement in the other direction is equal to 0 because it's also blocked, right? Obviously, if I increase the force, you can see of 10 to 7, right? obviously it's a linear problem. I should see that this number, if everything is going well, should become equal to 4.35, right? It's a linear problem. I increased the force of 10 to minus 7. Here, the previous solution was 10 to minus 7, right? I obtain the number. It's a linear problem, right? If you increase 10 to 7 the forces, you increase 10 to 7 the displacement. So, but this is only to show you a little bit about this, right? And you can see here, right, that the very important stuff is that you can have a plot of your structure, okay? Now, let me clean all the figures here, right? With 10 to minus 7, you can use this additional package, right? And you can see here, we can have the structure, we can have the structure with the load applied, we can have the deformed shape, and you can have the axial forces. If you want to know information, this package is called OPSVs. It's a very good package. Again, if you go from Opensees Spy, you can see here, there is a section called post-processing, the 13. Here you have the VFO. I don't use it so much. Honestly, I know very well the guy who did it, but I don't find it very convenient. But I mean, it's not meaning it's not a good one. So it's a personal experience as a user. If you go to OPSVs here, you can see the package, okay, and you can find the relevant information. Sometimes there are some problems, but the good things again is that it's an open code, so you can code the package and change by yourself. Okay, to speed up the discussion here, I think inside this folder, I will share you during the break together with the next class. You can find here another example of a truss structure like this. Obviously, I will show you only the Python code. The difference are minimal. In this case, everything is the same. The only difference is that we are defining 3 nodes, 1, 2, 3 with the relative coordinates. You are fixing, okay, you can see the different nodes. The node 3 is free to move. Yes, this code will be shared during the break. And you can see here that we are creating everything in a proper way. I can run again this code, and you can see that you can basically, where is this? Create your truss, okay? You can make truss as much complex as you want, okay, at this point by yourself, right? You can combine the elements, you can change the material. I think you can start with this basic one. Okay, let's move to the second example, okay? The second example is a truss structure. I think if you understood the first one, it will be very easy. We have a truss structure, elastic material. The cross section is B and H, and we have this truss structure. Okay, I will show you again, in the sake of time, okay, the Python code, but I think everything is the same. What is the only difference is that in this case, we have to move to a 3-dimensional space. We will see that when you want to combine truss and beam is a little bit more complex, but we will see there is a trick. We have again 2 nodes, right? Because we have the node 1 and the node 2. And in this case, we have a new guy. It's called the geometric transformation. The geometric transformation is telling you how to transform, okay, the load from the global reference system to the local reference system. In this case, it's a linear problem, so you can use always linear. We call this 1, okay? Maybe I should make a little bit bigger. And you can see you use the elastic beam column element. In this case, we are creating an elastic beam column element called number 1, connecting the node 1 with the node 2. Again, this syntax you can find in the TCL, Opensees Berkeley, blah, 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 or in the Opensees page. And we have a certain area, we have a certain elastic modulus. In this case, we have a certain inertia, and we have the geometric transformation. Surprisingly, the remaining part of the code is exactly the same. So if you remove the difference that here you have 3, obviously the inputs are different, but depends on the problem you are modeling. You have the geometric transformation, and you use an elastic beam column. If you compare the truss problem with the elastic beam column, you will find that everything is exactly the same. There is no difference. And you can see here, in this case, run the problem, okay? In this case, there is only a small difference here. I'm running steps increasing 0.25, right? And I'm performing 4 steps. And you have the well-known solution, okay, of a truss structure. In this case, this is your truss. You're applying a load 10. This is the deformed shape. Obviously, you can change the amplifier of the deformed shape to plot more or less ridiculous your deformation. And you can see there is no axial force. You can see very well. There is sorry, there is some delay. A shear force of 10. Remember, we are applying a force 10. And the bending moment, as expected, is linear. And there is some small numerical stuff. Obviously, this is at 0. You read -15, but obviously this is a numerical stuff. And the bending moment at the base is equal to 32. Again, it's depending on the units. When I say 32, that's the reason, because it's important to write at the beginning. This is Newton by meter, okay, for this specific problem. Obviously, if, for instance, I am applying a bending moment at the end, you can see you can change the loads by yourself, right? Let's change the load here applied at the end as a transverse. We added a moment, okay, as you can see here. If you add a moment, okay, the bending moment diagram you can do by yourself will be a little bit different. And since it's a summation of a constant bending moment diagram with a linear bending moment diagram, you are obtaining this. So what I did, I applied a moment equal F multiplied by L at the end of the beam, and I am obtaining basically this diagram. So if we go back to the previous one, I mean, to show you that you can change the load as you want, right? And for instance, I'm applying minus F here. What I will observe differently, I will obtain, obviously, and what I did, I add common dot more. Obviously, in this case, you will have an axial force, okay? So if you understand this simple example, I think we can move to whatever you want. I want to show you also a small, I mean, in really 1 minute without entering in details, that inside Opensees, that's very important, I think, for many applications. For me, it was important for my research personally. You can export the stiffness, damping, and mass matrix. So this means you can create your model and export from the solver MCK. And with MCK, you can do whatever you want then, obviously, right? You can solve. So the command you have to use is this one. It's called gimme MCK. I like the name. I think it's, if you go to the Michael Scott, page, you know, you will find some funny story about the song, right? Gimme, gimme, gimme. There is a famous song, right? He presented this command with the song. And you can see here, you can use this command and you can export, okay, the matrix K. And with the matrix K, I can show you for this simple problem. Let's see who is a good student here. For this problem, what is the size of K? Is a two-dimensional problem. Each node has 3 degrees of freedom. So we have 2 nodes, right? What is the size of the problem? In theory, it's a 6 by 6, right? But in this specific case, the node 1 is fully constrained. So you are removing these lines. They are not existing. So it's a 3 by 3, okay? So if I run the code here, okay, you will see that I can obtain, okay, the same solution. And here you will see very well, I don't know if it's big enough, you are obtaining the matrix 3 by 3, okay, K. In this specific code, okay, you can also calculate the different terms. Okay, here you will find, okay, this part of the code showing you the different terms of the matrix. Obviously, you have, if you remember a little bit about this, you have the different part of the matrix, and you can see here you have the different codes. Okay, this was the example 2. I think the other example I can go faster. And you can start to go faster. This is important for me. I think if you can speed up your coding capabilities is the best. Now, what about if I want to model this, right? That's frame 101, right? Everything is the same, right? If you learn, the first part is the same. The second part is the same. What is the difference here? We have to define 4 nodes, right? And we have to give the coordinates of these 4 nodes. And then we have to define 3 elements. In this specific case, I'm considering that all the elements, they have the same linear constitutive law, and I'm as well considering that we have the same cross section, okay? Let's open again the sake, because we have, the time is against us, but let's reach the right point. Sorry for this delay. Let's see. I lost the connection. Let's remove the VPN. Wait, so maybe. Share, yeah, maybe keep the VPN now that we are not using explicitly the website. We can keep out. Okay, you can see here what is the difference. I think you can understand, right? It's exactly the same. The difference is that we have 4 nodes, 1, 2, 3, 4. I think you can read the coordinates by yourself, right? The node 1 is 0, 0. The node 2 is 0, L2, right? The node 3 is, the node 2 is L2, 0. The node 3 is 0, L. And the node 4 is L2, L, right? So if we go back, you can see the node 0. Let's see if I point. The node 1 is 0, 0. Node 2 is L2, 0. Node 3 is 0, L. Node 4, L2, L, right? And you can see here, we are fixing. In this case, I mean, I don't know why here. How to read this? This is an inch, right? So it's 1, 1 with the rotation 3. If I do like this, I fully fix. And then you have the 3 columns. You can see here, 1, 3, 2, 4, 3, 4, and so on, right? Okay, so, and you can see here that you can basically solve this structure, and you can see very well that we are applying a load here, right? There is some delay. No, I'm clicking in a wrong way. Here we have the actual force distribution, right? We have the shear force, and we have the classical bending moment diagram of a frame. Now, obviously, I think if you can understand this code, I think obviously I'm not expecting in this class you fully understand this code. But if you can, I will share during the break all the codes, okay, for this and next class. But if you can understand this, obviously you have to change this part and you can make your code as complex as you want. So if you want to make a 10-story building with simple frame, you can make it, obviously linear elastic, right? And see the bending shear moment diagrams, okay? So here I think there is also the extension you will find, for instance, for 2 stories, right? If you want to see a 2 stories, you can see is again, everything is similar, right? The difference, let me make a little bit bigger this part here. Let's increase the font size. So you have, in this case, 6 nodes. 1, 2, 3, 4, 5, 6. You have the baser fully fixed, and you can see here the 1, 2, 3, 4, 5, 6 elements, which are 1, 2, 3, 4, 5, 6 elements. Okay. So now I think you can make complex as you want. Obviously, if you want to make the element 1, let me check which one is the element 1. Here we can read the element 1, the area of the element 1, half, right? It's very easy, right? You can change here, right? A divided by 2, right? I'm running the same example, right? With the element 1, okay? With the area half of the previous one, okay? Now, don't ask me what's going on. It's a little bit less intuitive for me, the diagram, but right, is a more flexible column 1 with the horizontal load, okay? And you can change whatever you want. You can define one area for each element. You can change. Okay, the final part of this lecture, I think I have 2 minutes. I would like to switch to the point 4. Maybe we can discuss about the next point after the break together with the 3-dimensional structure. Is, okay, let's save it. Is the case of internal hinge, right? This is a tricky case. I know many students are getting crazy with this. Generally, I'm using the equal dot in this case. So I'm putting a cinematic constraints between the node 5 and 6, right? We have 1, 2, 3, 4. We have to create 2 overlap nodes and join them. Okay, let's see in this case, how does it work? You have a code again. All the codes are both in TCL and in Python. So you can see here that in this case, let's see what I'm creating. Let me run the code. Everything is the same again. The only difference is that I'm creating node 1, node 2, right? 3, 4, which are 1, 2, 3, 4. And then here in the center, I'm creating two overlapped nodes. You can see they share the same coordinates called node 5 and node 6. And I'm creating, you can see, 4 beams, okay? The first beam is connecting the node 1 with the node 3, is the first column. The second one is connecting the node 2 with the node 4, 2, 4, 1, 3 is the second column. And then I'm creating 2 beams from the node 3 to the node 6 or node 5 on this. Let's say we consider 5 on the left side and 6 on the right side. So we have 3 to 5, you can see. 4 is connecting 4 to 6, right? 4 is connecting 4 to 6, right? And finally, I'm connecting the node 5 and 6 with an equal DOF. Equal DOF means that we are constraining the kinematic of the two nodes to be the same by saying that the nodes 5, 6 should have the same degree of freedom 1 and 2, which means the same translation in the x direction or horizontal direction, and same translation in the vertical direction. And different rotations are as I'm expecting in an internal hinge. As you can see, the deformed shape that plotted again with the OPSVis package, right, is exactly the typical one we are expecting for an internal hinge, right? You can see we have large rotation here, but we have the same vertical and horizontal displacements. This is the typical axial force diagram. We have the shear force diagram and the bending moment diagram, where you can see we have the zero moment in the hinge as expected, right? Obviously, we can make something more funny, right? We can, for instance, have the same horizontal displacement, for instance, and the same rotation. In this case, obviously, we let the structure to you can see here, to move or horizontally of the same amount. The two sides, they have the same rotations. Obviously, they can rotate of the same amount, but since we are not fixing the vertical displacement, the two vertical parts can move independently. Okay. Obviously, if I type here 1, 2, and 3, what I'm obtaining is the same solution of a frame where you can see I have full continuity. And you can see here, I have the shear force here, and I have the bending moment classical, okay, of a normal frame structure. Okay, with this in mind, I think it's time for the break. I think I exceeded of some 1 minute. I think that one is not aligned with my clock. I don't know which one is right. Maybe I'm wrong. Okay, some minutes. Yeah, okay, 2, 3 minutes. Okay. I think me and you were aligned. But I would like, I think it's a good idea to share the material with them. Another suggestion, if you cannot see very well the screen, you receive the Zoom link, okay? So you can connect with your computer, okay, here from Zoom and see the code, because sometimes I can imagine maybe the code, especially in the last rows, I think it's not easy to see the code, right? But my suggestion, you have the Zoom link, right, in the email, right? So you can connect to the Zoom and look also from your computer. Regarding sharing the file, maybe I can give this file now to Yonja, okay, and ask him to send an email. All of you guys can access to internet?
Yeah, they have free Wi-Fi for the second floor.
Okay. That's great. And I will share also the first exercise, okay, for the interactive session in the evening, okay? So, because if you can solve this, you can solve those exercises, okay? They're more complex than this, but the concept is the same.
I'm going to share the slides also.
Yeah, I don't have so many slides, but I mean, I will share the slides I have. And Massimo, I don't know, because you and they are installing something for tomorrow, and then we go on break. So you prepare some document.
I prepare some document and I can share with them.
Okay, maybe you can share with me now, so and we can share during the break everything. Because he's willing to help you to compile Opensees tomorrow, so you should download something in your computer, okay? Great. Okay, let's say, I don't know about the break. Where is the break? There is a coffee break.
Yeah.
So what is it?
There's a break. Take some rest. Yeah.
Okay. We can meet here at the, we want to say 11:05, okay?
Up to you.
Yeah, 11:05, okay. We don't want to kill them. Also 11:10, yeah.
Okay.
11:05.
So maybe.
Hello. Okay. So you can scan this code maybe you can take a photo of this and you can connect to Zoom, okay? In theory, you received the Zoom link by email, right? You received an email by the info, yes. Okay, but if you want, you can follow. I think for you, probably it's not needed on the first row, right? You can see the screen from here. But for the people, I think in the last row is a little bit more complex to follow what we are talking about. Okay, we have something like, let's see the message, if something is happening, the files. I think we have a cloud. I don't know if you received the cloud. Okay, let's do the same with the cloud. You can try by yourself. In theory, this link should send you to the cloud. They created a cloud, so you can download the material. Is okay? Can you use this link? Or in theory, you will see this link on the chat box. Okay, with this in mind, let's continue our discussion. I think you should have received the different parts. And basically, let's recap what we did, okay, following the content of this folder, okay? First, we introduced a little bit TCL and Python. I hope that we learn what is TCL and Python. We learn as well where to find the information, okay? Remember those two websites are very important, okay? The website of Opensees by Berkeley, the website of Opensees Pi. There you can find the relevant information about the syntax and how to use the code. We start to solve a very simple trust structure, okay? It's a linear elastic trust structure. We learned that the code is divided in several parts, okay? First, you have to define first we wipe, then we define the different variables, defining our problem. For instance, in this case, the elastic modulus, the area, the length, and please mute your computer or we will have some weird echo. You can see here, we apply a certain force at the end. So we define this, then we start by the definition of the model builder. In this case, we use a 2-dimension 2 degree of freedom for each node. We define the location of the node with the tag is the name. Then we define the element, we apply the force. We define a setting for the solution. And then we obtain certain solution. We set the recorder, okay, in order to save some information, or we can get this information in real time in Python. And then inside TCL, we can plot certain information or save an external file. You will find this external file when you run the code. Or inside the Python, you can have also post-processing. I suggest you to use OPSVs, but if you say that OPSVs is impressive when Massimo will show STKO, I mean, then you can discuss about the money with this gentleman. But I think you will be more impressed about the capability of visualize and your model. Okay, in any case, this is what we learned. Okay, we learned that if we can understand, I don't know who is typing on my screen, if we can, how to remove this? Annotate, clean. Yeah, remove. Okay, we learned that basically, if we know how to solve this, is a trust with very simple modifications. What's going on? I don't know why I cannot click on my computer. That's new. Huh? So with very simple modifications, okay, we can model this. The only difference in this case is that we are using a 2-dimensional model with 3 degrees of freedom, okay? In this case, what is the only difference is that you need to run Spider until there is some community online, start to help each other, right? That's good. Okay, we have only to change to 3 degrees of freedom, and we can use the elastic bin column element. And in this case, we learn that if we can model this in a very, very easy way, right? We can make a frame elastic, okay, like this. And after you know how to model this, okay, you can model structure as complex as you want with their linear elastic beam, okay? What is the limitation of what we have seen until now? That everything is like this, in 2-dimension, right? Okay, as engineers, it's very common to run 2-dimensional models. I have to say, in my research, majority of the models are 2-dimensional because it's a good simplification and you can understand much better what's going on. So always, when you start something, I mean, more research-oriented rather than obviously structural design oriented, my suggestion is start with a 2-dimensional model. If you can understand the 2-dimensional model, then move to the 3-dimensional model, okay? But in any case, obviously, Opensees has full capabilities to model 3-dimensional system, okay? But we have to understand a little bit some tricky stuff, okay? Before to move to the 3-dimensional, I want to complete the example of this morning, showing you another case, okay? This case here, okay? When you want to join, okay, this is a typical problem, and you will have this in the homework. So when you want to make a small house, right? In this case, we have 2 elastic beam column, okay? And we complete the 2-dimensional, basically, space. And this 2-dimensional, we have 2 beams in the 2-dimensional space. We have 2 elastic beams, the element 4 and 5 are 2 elastic beams, and then we have a truss. You can imagine that's a roof, right? Made of 3 elements with 3 edges. We have 3 nodes, 1, 2, 3, and then we have this. So what is the difference in this case with what we have seen before? That we have elements working in a 3 degree of freedom, right? The beams. Because the beams, they have the action force, the shear force, and the bending moment at the end. So you have 3 basically kinematic conditions for each node, satisfied by internal stiffness of the element. But when you move to the truss, you have only the axial force, or if you want, in the global reference system, you have 2 components projected in the global reference system. But you don't have any bending moment. That's the definition of the truss, right? A truss is an element without bending force. So this means that you have an element that should work in a 2 degree of freedom per each node. So in this case, the solution is relatively simple, okay? Let me show you first one example, okay, to complete. Let me see here, let me close this to make some cleaning. I don't know what's going on. I think I changed the name of the folder like an idiot and I destroyed my computer, right? No, yes. Save, no, okay, yes. Okay, let me restart with this example here, okay? So I want to show you this example, okay? We want to create a truss, okay? You can see here. A truss similar to, let's see the truss I want to create. This truss here, okay? So it's 3-element truss, okay? And this truss, you can see 1, 2, 3. We want to build the same we did before in a 3 degree of freedom space, okay? We say that the problem in this case is that we don't have the rotation of the truss. Okay, what's going on? If I run this code, you can see. So I basically, what I'm doing, if I am not an expert in finite element and then I'm not an expert in Opensees, what I'm doing, I'm creating the constraints, right, like this. So according to the model, I'm fixing in the node 1 the vertical and the lateral translation. I fix the node 2, for instance, like this. I'm doing a statically indeterminate system. And then I keep free the nodes 3. And I keep free the rotations, right? So if I'm doing like this, you can see what I will get is the following error, right? Let's see. You can see this warning here, right? So it says ban SPD limpac solver, an error on solve, factorization failed, magic singular, right? Which means basically Massimo will say that the structure is unstable. That's in English, it's not unstable, but is statically indeterminate. or yeah, unstable basically. Yeah. Yeah, you're right. It's unstable. Yeah. That's the time of sleeping. Also for me, that's the time late. Yeah. Unstable means that the number of, I mean, you can have two types of instability, right? Let's go back to structural mechanics, right? The first case of instability is when you have less constraints than the number of equilibrium equations you want to write. And this is the case. The second case is because you have improper location of the constraints. Okay, in this case here, the problem is the following one. You have, let's go back to the figure. In the space that you set, you have that the node 1, 2, 3 are built with 3 degrees of freedom. The 3 degrees of freedom are the translation along the global x, shown with the red axis, right? The translation along the y-axis, and the rotation basically in the direction outside the space. Okay? When you use the truss element, the truss elements, they have a stiffness matrix expressed by 2 by 2. So they don't have any rotational component. When Opensees is assembling the global stiffness matrix, basically whatever is going on is that all the nodes, all the degree of freedom connected to the rotation are free. So you have all the lines and the rows, so all the rows and the columns of the column of the stiffness matrix M, which means unstable. So in this case, basically, if you have this condition, what is the problem? You cannot calculate the inverse of the matrix. So, and for this reason, Opensees is getting stuck. Or if you want, the solver of the matrix is not Opensees in this case, right? So, and you receive this error. Remember, this is a very common error. And it's telling you that the structure is unstable. When it's unstable, obviously it's hard to think why the structure is unstable, okay? In this case, I mean, we can solve this problem by blocking all the rotational degree of freedom. So the rotational in the fixed is the third component. So if I have 1, 1, and 1, also of the full free nodes I'm blocking the rotation, you can see I can run this and I can obtain the well-known solution. I mean, it's a simple truss with a horizontal force, right? You have this is not loaded because I'm blocking these two nodes. Obviously, the reaction is fully absorbed by these two constraints. So I have 0 actual force on this strut element. And you can see I have the well-known element here. The force is moving from left to right. So this is under tension and this is under compression. Since the inclination of the two truss elements is the same, it's also symmetric, right? As well known. It's simple the projection of the force in the two directions. Okay, so please keep in mind that if you want to build the house, as we have seen before, right? This house here, you have to apply the same approach. So in this case here, I think you have this, right? You can see that you have the elastic, sorry, you have the model builder with 2 dimension and 3 degree of freedom. You can see here you have the 5 nodes of the model we have seen before. We fix the different parts, but you can see we are always fixing the rotation, except I will show you in the model these 2 nodes. And first we are creating the elastic material, then we are creating our elements. Okay, the truss here, I'm creating 2 elastic material. Please keep in mind that you can create as many materials as you want, for instance. If you don't use the material, it's fine. Okay, you don't have to use all the material. That's not true for the nodes, unfortunately, right, Mas? For the nodes, if you don't use the nodes and you don't connect to something, right, then the structure is unstable, right? But for the materials, you can create as many materials as you want. Then if you don't use it, who cares? Similar for the geometric transformation, right? You can create 1 million geometric transformation. If you don't use it, it's okay. Okay, in this case, you can see if I run the code, I will obtain, you can see here, this small house, right? It's a very ugly house. I don't know if you have friends from architecture or some of you is from an architecture department. It's a very ugly house, but you can see it's a simple house. You can see with 2 elements and 2 elastic B column elements and the truss on the top. So now I have a question for you, right? As you can see here, let's see if you are following the discussion. So I'm fully blocking the node 4 and 5, right? Obviously, this is the base, right? They are simulating the foundation of our building, right? Never discuss with a geotechnical guy saying that you model a foundation as a fully support, right? I hope we don't have many people from the geotechnical community. They will be very disturbed, but in the structural engineering community, always we fully fixed, right? We like this concept. Obviously, it's totally fake fully fixing, right? So we know it's important we know very well and we accept this, but it's a good proxy for the solution. We have the two elastic beam column elements. As you can see, I'm blocking the node 3 in terms of rotations. So I'm leaving free the two displacements, horizontal and vertical displacements. But why I'm not blocking the rotation of the node 1 and 2? There is a simple reason, because the node 2 and 3, the node 1 and 2, these two, are stable because the rotational stiffness is coming from 4 and 5. They are the elastic beam columns, okay? So you don't have to block this rotationally, right? Because the rotation of the node 1 and 2, the rotational stiffness of the node 1 and 2 is coming from these two elastic beam column elements, not from the trap. This is different from the case before, right? In the case before, the case without the elastic beam column, we blocked because there is anything able to block the rotation. In this specific case, we have two elastic beam column. You can see, and they are able to block the rotation of this. I can see in the chat is happening a lot of things, right? Let me only have a look. I think they are helping each other, right? Good. Okay. Any question about this? It's clear? Okay, keep in mind that when you are joining elements of different dimension is always a problem. Another typical problem, we will not discuss in this because it's an introduction, is, for instance, and Massimo is an expert about this, how to connect a beam with a shell. So when you have a shear wall modeled by a shell, right? And I think it's a similar concept in some sense, right? Because you have elements with different dimensions, right? So when you have elements with different dimensions, remember, you should think a little bit more. Okay, let's start, with the conclusion of this. I think we basically, I think you received this folder, right? Okay, so we did 0, 1, 2. I will skip this part, it's not so important. It's only, some detail you can find how to apply a cinematic constraints, but we will see in a 3D. And I think we can move to a 3D beam, okay? Okay, make 3D structure in Opensees generally is a nightmare at the beginning. I know all the people are trying to make something 3D is complicated. So what is the difference, do you think, between a 3D and 2D structure? One is in 2D, the other one is in 3D, right? But I will ask my friend to help me. This is put like this your head, right? No, you can see it. Put it like this your head. Okay. Yeah. Okay. Okay. Don't be shy. Okay. You're not helping me. Okay. This is your cross section, right? Okay. Let's say it's rectangular, right? You have B and H, right? So this means that if you want to calculate the inertia in this direction, you have B multiplied by the cubic power of H divided by 12, right? In the other direction, you have to switch B and H. Okay? When you are in a two-dimensional world, right? Like this is a two-dimensional world, right? In a two-dimensional world, your cross-section can be only like this. There is no discussion, right? You calculate your inertia, and your cross-section must be like this. There is no discussion, very simple. When you are in a three-dimensional, be happy, come on. When you are in a three-dimensional world, right? Your cross-section can be like this or like this, okay? Or can be also like this, right? Can be whatever you want. Obviously, your cross-section cannot be like this. So the only condition that you must respect is that your cross-section is, this is the beam axis, okay? The river can cut it like this, right? So then you will start to flood, right? So it's a nice experience. Okay, so you can see the only condition we must respect is that our cross-section is in some sense orthogonal. So this is exactly what we have to discuss with our friend Opensees. I hope it's becoming our friends like we are friends, right? Okay, no, this is yours. we have to explain to Opensees how to place the cross section. Okay, that's it. Okay, let's assume we have a rectangular cross section. Okay, again, elastic material. How to explain what is the orientation of your cross section? Do you remember we said when you introduced the beam, I said we have this geometric transformation? Okay, geometric transformation is a very powerful command because it's doing three things. In one-dimensional is explaining only, in two-dimensional is explaining only how the local and global reference system are transformed, okay? And that's relatively simple. In the three-dimensional system, is providing information on how your cross-section is oriented, okay? So the geometric transformation is explaining how the cross-section is oriented. If you think it's the same concept, because in any case, you are creating a connection between the local reference system and the global reference. In this case, and in this slide specifically, this is your local reference system. In Opensees, generally, Y and zeta are the cross-section local reference system. X is the element axis. Okay, you don't see it is going out from the whiteboard. And then we have a global reference system. Okay, so let's. I have to solve this. I don't know what is this. Online, there is a problem for me, guys. If there is a problem for me, please maybe write Chris and then the question. Okay, so I can follow it. It's for me also we are discussing. I think they are solving some problem. So we have the global reference system. So in this global reference system, three-dimensional, we want to have a beam. Okay, you can see it's exactly the same as the example, the first example with the elastic beam column we saw. And we have two forces, F1 and F2, oriented in the global zeta direction and the global X direction. And you can see, obviously, the element is along the Y-axis, okay, put with the node 1 with 0, 0, 0. And obviously, the node 2 is located at 0, L, 0. Okay, so what we have to explain to Opensees, I think, following this example, if this is your cross-section, if the cross-section, okay, is located like this, okay? I'm trying to explain. I'm sorry for audience online, but I think if the Y local axis is lying in the zeta global direction, or if the Y local axis is lying in the X global direction, okay? Obviously, you can have also different angle, okay? What is the best way to explain an orientation in a three-dimensional space? A vector, okay? So what we are using a vector to clarify the direction. So generally, you define your cross-section in Y and zeta reference systems. And then if you define the vector 1, 0, 0, this means that the zeta, okay, the zeta is the king for, I made the example with Y, but the real guy with the boss is the zeta. The zeta is the local zeta is lying in the X, okay? 1, 0, 0 means X direction, right? Okay. If you lie this axis in 0, 0, 1, this means that the zeta local axis is aligned with the global 0 axis. Obviously, if you type 1, 0, 1, what does it mean? That the cross section is 45 degrees, right? Okay. Again, if you make 1, 0, 0, okay, and minus 1, 0, 0, for our problem is the same. For this problem, it's not always the same because your problem is an elastic section, symmetric in the two sides, right? So you don't have any asymmetry. But for instance, if you create a fiber-based cross-section, you will see this happen. Okay, some non-linear stuff. Imagine a reinforced concrete cross-section, right? If you have the reinforcement different on the two sides, if you place the cross-section like this, or you place the cross-section like this, the result will be different. Okay. For our specific case, the orientation is useless. You can do whatever you want. Okay, let's go back to the code. Okay. Any question about this? It's clear. Obviously, here you will see only the local axis are switched in the slide to explain, okay, how to move from one reference system to the other reference system. I'm sure for the audience here, you are expert in structural engineering. It's well known that F cubic power of L divided 3 EI is a solution of the cantilever beam subjected to a transverse force applied at the top, okay? That's well known. So what is only changed here is the axis of the inertia, or if you want, the way the cross-section is located. Okay, how to do this inside Opensees, okay? Let's open our code, okay? And let's see, what is the difference? Again, is I like to show you the difference because if you can understand the basic, it's easy. Again, everything is the same, right? Not exactly, right? When you want to make three-dimensional, right, you need to calculate the inertia in the two direction. Obviously, B and H are switching in one direction and the other direction. In this case, it's a square cross-section, right? Is a 5 centimeter, right? The units are meter for my case, right? So it's 5 centimeter, right? And the BH cubic, HB cubic, maybe I can zoom a little bit to be sure that you can see better. And then we calculate J, okay, the torsional stiffness, okay, but I mean, for our case, we don't have any torsion, but potentially, remember, in 3D, you can have also torsion, right? So in this case here, we have F1 and F2, right? We are creating the model. The difference compared to before, you can see is like we are creating a three-dimensional model, right? With 6 directions. Then we have the node 1 and the node 2. We have 0, 0, 0, 0, L, 0, right? Are the coordinates, right? We are putting our structure in the global y direction. So this is also very important. Try to, before to model, try to sketch your structure, okay? I don't say such a fancy sketch. I did this with Illustrator, okay? But also with your paper, okay, in front of you. First, make a figure of your model, okay? This is helping you a lot to understand what you're doing before to start to code. In a majority of cases, that's a discussion, I mean, between not relevant for this. My main problem with the students in Opensees is not the coding or the programming, it's that they don't know what they want to code, you know? So first, try to know what you want to code, okay? That's very important. Okay, anyway, so we have this structure, okay? The y-axis is lying in the y direction. And you can see here, we fully fix the base. In this case, we have 6, right? This means we fix the translation along x, translation along y, translation along zeta, rotation along x, rotation along y, and rotation along zeta. Obviously, these are referred to the global reference system. So we fully constrain, we block our beam. So it's a cantilever beam in the vertical direction, but I mean, it's a cantilever beam. The second node is fully free, right? And you can see we have, different from the exercise in the 2 dimension, we have these 3 numbers after the geometric transformation. These 3 numbers, 1, 1, 0, whatever it is, are the vector explaining you, providing information you, how the local zeta, okay, is oriented in the global reference system, right? Okay, what do you think if I'm writing this vector like this? 0, 1, 0. Is this possible? I need you again. Yeah, but woman shouldn't be, right? Oh, bro. Okay. If I do like this, where is oriented this cross section? It's oriented like this. It's possible a cross section is like this. What do you think? No, makes no sense, I mean, right? If you can understand how a beam is working, right? It makes no sense, right? Obviously. So this means it's not possible to have a beam like this, okay? So, and if I run this, in theory, let's see, we should have an error, right? Let's see. I mean, I don't know why I restart the kernel, but I think obviously you have an error, right? Because the cross section cannot stay like this, right? It's impossible, right? So simple, when it's making the projection, because mathematically it's doing the projection of the 2 vectors, basically it's not finding any possible solution because the vectors are parallel. So the cross section is parallel with the cable axis. It's not possible. So if I'm doing this solution, right? You can see I can easily run my code, and I have my three-dimensional beam. Here you can see a representation of the three-dimensional beam with the deformation, okay, and so on. But you can see very well that I can use the equation that I have shown you before, right, to show that the two displacements are okay, okay? So what we have to learn is this important concept, okay? The only difference for an elastic structure between two-dimension and three-dimension is that in the geometric transformation, we have to add the information on the cross-section. My suggestion regarding the convention is to play a little bit. So what I want to say, in this case, obviously, the two displacements are the same. Why they are the same? Let's look at the input. So I'm using, you can see, a square cross-section. So what does it mean? If the cross-section is square, the two inertia will be the same, right? And what about the force in the two direction? They are exactly the same. So if you play by yourself, okay, to learn the convention with this exercise, first you can change this and create the two inertia, right? Because these two inertia are then included in the element. You can see when we create the element, obviously, another difference is that we have J, G, AY, and I zeta. We have the two inertia, right? J is the shear modulus, J is the torsional stiffness, but basically from us it's not adopted, right? And you have the two inertia. So you can change the order of this, whatever you want to do here, and you can basically change the things. For instance, if I'm making this 2000, right? You will see that in this case, the displacement is working with the convention, but obviously I have more displacement in one direction than the other direction. Similarly, if I create another asymmetry by change the stiffness, okay, for instance, let's make this section 005 by 005, right? You will see here that I increase the displacement. You can see the displacement in one direction compared to the other, okay? So you can play by this basic example, right? And try to understand or get familiar with your convention, okay? So once you know how to model this, right? You can move to something a little bit higher level, right? The typical higher level, right, is the reported in the exercise 7, and is what I'm calling the table. The table is the frame in 3 dimensions, right? This is a very long table, right? We have an almost square table. Okay, in this case, it's exactly the same. We have 1, 2, 3, 4 elements representing the columns. We have 5, 6, 7, 8 representing the beams, and we have 8 columns. The logic is exactly the same, right? We have to define the columns, 1, 2, 3, 4, and we have to define the beams. Obviously, if you think in this problem, you cannot have the same geometric transformation for all the elements. Because all the elements are pointing in the 3-axis, right? So at some point, if you use a geometric transformation, you will have some parallel cross-section. So what I want to say, for the beam, maybe you can use this geometric transformation, right? But if you use this geometric transformation for the element 5 or 7, then will be parallel, right? So if you use this geometric transformation, it's okay maybe for some elements, but it's not okay for the other one. So you should decide one geometric transformation for each of these elements, okay? Or at least for each of this class of elements, okay? You cannot use the same. Remember, you can decide how many geometric transformations as you want. For instance, also one for each element. Or you can also have more geometric transformation than the elements, because there is no problem if you don't use it, okay? So this example is very simple, okay? Is very, very similar to the previous one. Let's run, to see the model. Maybe also here is useful to see the model. That's the model, right? You can see we have to define the inputs. I will not spend any time on the inputs. Obviously, I'm assuming the same cross-section for all the elements, but I think it's easy for you to change by yourself. So if you want for each element, you can define a cross-section. You are defining the 8 nodes. I think it's simple by the variables that you have seen in the previous slide. So L1, W1, and H1. These are creating basically a cube. A parallelepiped with the different sides. We fixed, again, the translation along X, Y, Z, the rotation along X, Y, zeta in the 3 directions, right? And basically, we create what the geotechnical friends they don't like, right? Is these three-dimensional, right? Conditions here, fully fixed. And we have 7, 8, 5, 6, 7, 8. You can see this nodes free. Then we are creating three geometric transformation, linear. As you can see, you can create a string and then copy the string here. And you can see here, we can create different geometric transformation according to our needs. For instance, we can create a geometric transformation called 1 in the X direction. I don't know why in this code I have, maybe I was playing with some other example. So let's leave 0. You can see this is in the zeta direction, this is in the Y direction, and this is in the X direction, okay? And you can see here, we can associate these transformations here to the different direction. For instance, the element 1, 2, 3, 4 are the columns, and you can see I'm creating a global, I'm creating the local zeta axis is lying in the Y axis, okay? And I'm using for the beams the direction, the zeta global direction, okay? Okay, so in this case here, you can see, let me run again, is very important, and you will see in this example, you can also provide a three-dimensional representation of the cross-section with OPSVs, okay? So you can have a look about the cross-section. Intentionally, as you can see here, I made the cross-section very elongated. You can see the base is 0.5, one direction is 0.5 half meter, and the other one is 10 centimeter, okay? So in order to see the orientation, okay, that's the reason because I make the cross-section very elongated. And obviously you can see that the cross-sections are pointing, the columns are pointing in the Y direction. So I'm using the tag Y here. And the tag Y here is pointing in the Y direction. And for the columns, you can see I'm using the zeta direction. And you can see that the elongated direction is pointing in the vertical direction. Obviously, if, for instance, I'm changing this, right? So I want to make the column, right? The columns to be 45 degrees. I can make 1, 1, right? I can rerun this code. So now you can understand why you have seen 1, 1 there. And if I go to this row, you can see that now the columns are oriented at 45 degrees, right? Obviously, by playing with those two numbers, you can obtain whatever orientation, right? Okay. So then, I mean, everything is the same. There is no difference. The code is exactly the same as what we have seen for the two-dimensional case. And you can see here that you can store your information, you can save, you can reapply load, you can do many stuffs, and you can plot. Only a minor things is that from line 129 to 136, okay, you will see this code. This is something inside the OPSVs for plotting this three-dimensional stuff. You cannot plot at the moment, but maybe you can develop something by yourself, okay, in the package. You cannot plot whether a cross-section, I think you can have circular, square. I think circular and square, if my memory is right, but you can have a look, or we can have a look if you want on the website. The code is called, what is OPSVs, OPSVs? I forgot, I think it's circular and rectangular. Let's see whether a cross-section defined. So, no, they have also the I cross-section. I remember they had a third one. Circular, okay, you have only the radius. Rectangular, you have B and H, and you can have also I cross-section, and I think you have some variables. Honestly, I never use the I cross-section, but it's only to visualize the cross-section. I think it's useful to provide these plots. Okay, what is the problem in this story? I think everything is clear. You can see the example. Again, I will be here for the next 2 days, so I'm happy to discuss with you about code if you have a specific issue. What is the problem? So who is you think to be a strong structural guy? So what is the typical assumptions? What is missing in the table? The slab. Generally, if you study structural engineering, you should know that generally we don't model a structure like this. We use a rigid frame, right? Rigid diaphragm, right? We call it. So this means we are considering that the slab is so stiff compared to the frame system that the points, this, are kinematic constraints. That's a common assumption in structural engineering. there is also a big discussion. I mean, if this is true, it's not true. If you move to masonry structure, this is less true. But if you move to real, to normal reinforced concrete structure, that's a very common assumption. So Opensees is giving you the opportunity to define a rigid diaphragm. And in this case, the difference from this table to, I think only, let me see. I think you have another example, okay, only to complete the example you will find in the folder, okay. It's the same, but you have 2 stories, okay. Okay, now I think obviously if you want to build, okay, you can build as much complex as you want. But let's go to the rigid diaphragm, okay, rigid frame or rigid floor. No, what is this? Rigid frame. Okay, in this case, the model is exactly the same, right? So what we are doing is to assume that your rigid diaphragm, okay, is providing fully kinematic constraints between the node of the top, right? You can define 1 for each story. And what you are defining generally, and that's common in earthquake engineering, you are defining a node where you are applying the loads. So since the nodes are fully constrained, there is no behavior, dynamic, let's say, transfer of force, except like a division, right, according to the distance from the points, because it's basically the rigid behavior. You define what is called the master node, okay, and then you have a series of slave nodes located on the slab. Generally, the master node is located on the centroid of the slab. I mean, that's another complex stuff, because the centroid in theory is the, from elastic perspective, but I mean, we are entering now in a more practical discussion, is the center of stiffness, we call, right? The elastic stiffness, because this center can change during nonlinear behavior. But generally this one, because this, the position of this for asymmetric structure can produce the torsional effect on your frame. Okay, how to build this? I think I will try to show this, and then I think this should be in the rigid floor. Let's open this code, right? Okay, the code in this case is exactly the same, right? Everything is exactly the same. The only difference is this one, you can see, is line 57 and 59. Let me zoom a little bit. First, we are creating the node number 9. Remember, the node 9 is the what we call the master node. In this case, the center of stiffness, but also the geometric center is correct. They are the same unless the columns are different. Okay, if the columns are different, it can be different. But for a fully symmetric system in terms of stiffness and geometry, is located on W divided by 2, L divided by 2, H, the location of the slab. So we are creating this node here called number 9, okay? And you can see we have the number 9 located here. And then we are blocking the master node, because otherwise we have again the same problem of instability. So the rigid diaphragm is basically a constraint, like 2-dimensional constraint, creating a block in the plane direction, okay? So you don't have any block in the vertical direction, and you don't have any block in terms of these rotations, right? So we have to block certainly the vertical direction, right? So you can see that first 0, 0 is free. Why 0, 0 is free? Because the rigid diaphragm can rotate like, sorry, can move like this. This is a movement, the first one, okay, in X and Y direction. Then our rigid diaphragm cannot move vertically, okay? Or the master node in the rigid diaphragm cannot move vertical, because otherwise it's free, right? You can imagine there is, you should always thinking if there is something can provide the speed. In this case, the diaphragm is making the node free. So we are blocking, you can see the third one, right? The third one means the translation along the vertical direction. Then our rigid diaphragm cannot rotate like this, right? So it's something we don't accept, because this node is free or is not blocking the rotation in this direction. So this means we are blocking the rotation along X. The rotation along X is like this, and the rotation along Y is like this. Obviously, I'm assuming X is in this direction and Y is in this direction, right? So, and we block this too. We have 1, 1, and our slab can torsional move. That's the main reason of this rigid diaphragm, right? We have this torsional 3-dimensional effect, and I will show you in a while this torsional 3-dimensional effect, we are leaving free. So we have 3 degrees of freedom of the master node, 0, 0, 0. You can see here they are blocked. And we are defining the rigid diaphragm with this node. First, we make the rigid diaphragm. This is the perpendicular direction to the slab. In this case, the slab is oriented, is lying in XY. So the orthogonal direction is theta, which means the number 3 means theta. Now, I don't know, Massimo, if you have a solution, but I think the rigid diaphragm can only be orthogonal to the global reference system XY theta. You cannot make a rigid diaphragm at 45 degrees.
Through the code, yes, you cannot do their
Yeah.
properties.
You cannot do, right? That's a limit. I don't know why, but I think you can only refer to X. So this means that the diaphragm must be oriented in X, Y, or like this. You cannot have a rigid diaphragm at 45 degrees. I mean, that's a limitation of the code. I think it should be easy to change this, right?
It's
No.
only because the multiple constraints are defining global system. So if
Yeah.
you want to couple 2 different degrees of freedom, you need a kind of constraint that is not available in Opensees.
Yeah, in fact, you cannot do it. You confirm
You
me.
can do it with penalty.
Yeah, that's another story, but you cannot do with
You cannot
rigid
do it.
diaphragm. At the moment, in 90% of frame structure, that's, I mean, sufficient. But in some case, for instance, if you have a roof incline and you want to make a rigid diaphragm for this roof incline, you cannot do it, okay? Only to let you know that there are some limitations. No, I was asking him if it's easy to implement because it's more on the implementing side, right? Okay, anyway, so you can see here, you cannot define this. And you can see 9, and then obviously this the first is the master node, 9, and the other one are the slave node. You can see 5, 6, 7, 8. I think online there is a big discussion about all this on Python, right? Okay, anyway, 5, 6, 7, 8. So they are the slave nodes, and we create the rigid diagram. As you can see, the remaining part is exactly the same, right? You can see very well I left exactly the beams and the columns. I can run and I'm applying, sorry, maybe to be clear, the force in the master node, as you can see here, right? You should apply the force. In this case, I'm applying a force you can see in the X direction. So if I run the code, we can see here, obviously I'm expecting you can see a displacement in the X rotation, right? So if I'm applying let's say let's say 0 forces, where I'm explaining a displacement here, nowhere, right? Let's rerun everything. So the structure will not displace, right? Because there is no force, right? You can see that the deformed shape is the 0 and I have no force. So, but I like always, I think that's my, I like to do this. F multiplied, why F is not existing, we call this F1, okay? F1 multiplied by, how we call L1. No, how we call the distance? L1, yeah, why is saying error? Okay, in this case, what I am applying, oh, sorry, I want to do, okay, here I want to do, sorry. Let's see if you are sleeping or not. So what is this, what you are expecting here? I'm applying a moment to the master node, right? So you will see that my structure is having, I like this figure personally. I don't know if you have the same feeling, right? But I really like this, to see this torsion, right? It's like in your table, you're applying a torsion at the moment, at the base, right? Okay, I mean, now if you understand this, you can make how many complex you want, right? You can make another story, you can make the slab different, okay? But that's the basic element. Obviously, there are some earthquake or structure engineering concept, right? What I was trying to explain in 2 minutes, but maybe it required for a seismic engineering class is where to place this master node, right? Because this master node is then changing the torsional behavior of the structure, right? Okay. Okay, with this in mind, I think I finish my class here. I think you have everything, okay? I think you have also example with 2 stories here. You find also something about how to run Opensees with MATLAB. I think someone asked me how to make a plot in TCL, or you can go at the end of this class to this gentleman. But I think they don't have to give money, right, to you, because they will have the TKO for free. Now I forgot, right? Yeah. You will have a TKO for free, right? So that's a possibility. Obviously, for people like me, with this lovely Apple, you know, SDKO is not available. But if you are a Windows user, it's available. I think it's SDKO is in English, right?
Yeah.
Oh, but it's not. There is an Italian version of it. No,
No,
only
we
in
didn't do
English. That's good. Okay. Okay, so you can run SDKO without any problem. They don't have a Chinese version, but maybe now we can discuss. We can promote a Chinese version of SDKO.
Actually, the Chinese guy was giving
Translations?
Yeah, webinars and stuff.
Where? In Bilibili?
Bing, I don't remember. I think it would be here at the conference.
Okay, on Bilibili maybe Steven did.
Probably, I don't know.
You know Bilibili.
No, he told me that.
You're not Chinese
there's
enough.
some Chinese-
You're not. No, Bilibili is like Chinese YouTube.
Okay, probably.
Okay. Yeah, yeah. Okay, so I think you will find also this. You can see this is a MATLAB file where we created a very simple. It's called FM functions. The reason of is a small package for plot inside MATLAB. Okay, so it's basically a copy of Opensees inside MATLAB. You can see you can define your elements, nodes, everything, and it's creating a TXT file, okay, an SC file, and run this inside Opensees, and then it's providing a three-dimensional output showing the format, shape, bending moment, and so on. Okay. Again, this is limited FM. Sorry, only to give the credits. Is the reason it's called FM is because it was made by a guy, Francesco Marmo, from University of Federico II of Naples. So I think it's very simple. Obviously, you can see all the code, and you can have a general idea. So you have this option. Also to run your code through MATLAB or learn how to run your code through MATLAB, like this gentleman here, right? I forgot your name. Repeat your name.
Yeah.
Leah, very nice. Lee is your family name, right?
No, Maria.
Malian.
Yeah.
Ah, you're Mal, like you're an orc.
Of course.
Yeah, good. Yeah. Very good, very good. Okay, with this, I think it's time for Stefan. Stefan is more important than Opensees. Again, if you have any question, I will be available also this afternoon for helping you installing and try the access. Antonio, I don't know if Fabio, because Fabio is mainly using slides. Yeah. So I don't know if we want to share before.
Yeah, I think it's uploading the cloud.
Baidu Cloud?
Yep.
Okay, so you will have the slide before, okay?
Yeah.
And for me, with today we finished. No, I think we will meet again with me and Antonio Sberna for the applicative example, okay? This in the evening. And we will meet again tomorrow with me, and tomorrow morning you will have the dynamic part as well with Antonio, right? Okay, now it's time for Stefan, right?